Hello, everyone, and welcome to the May 2023 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. Those of you who are regular listeners will remember that last month, we do the AMA episodes every month. We do episodes every week, but once a month, it's an AMA episode. And so the April 2023 episode, we began with a story about the March 2023 episode. The March 2023 episode, I started off by talking about the fact that it had been really hot in Baltimore over the summer, and I sort of jokingly, or at least not very seriously, connected that to climate change and how it affects people's visceral reaction to these scientific findings. And people didn't like that. So that particular podcast episode was much higher audience numbers on YouTube, of all places. Regular podcaster listeners didn't care. But on YouTube, somehow people were funneled to listen to that. I guessed it was because of me mentioning climate change, because it got terrible reviews, that episode. It got more dislikes than the typical episode. And also there's a bunch of weird people in the comments complaining about climate change and scientists. So to do the experiment last month, I also talked about climate change in the intro, wondering whether YouTube's algorithms would somehow find it once again, mostly for fun. Like, I'm not actually going to be doing this as a regular thing to try to get more engagement. Anyway, the experiment was a complete failure. Actually, that's not true. The experiment wasn't a failure. Experiments are only a failure when you don't get an answer, when you don't learn what is going on. But the hypothesis that by talking about climate change in the intro, I would drive engagement, that was falsified by the experiment. No more than the average number of viewers/listeners, etc. So I don't know. I don't understand what makes people find the podcast on YouTube. For that matter, I don't really understand what makes people find the podcast at all. I wish I did. I would like to bring the word of the podcast to more people. I think I'm talking about it all the time and everyone knows that I have a podcast, and yet I'm still constantly running into people who in my mind would be very natural audience members for the podcast who don't know that I have a podcast, who've never heard of it. So I don't know how to get the word out there. I gotta be a little bit more systematic or scientific about these kinds of things. Otherwise, that's it. I have no great words of wisdom for the intro here. We have lots of questions to get to. I will just offer the standard reminder that these AMA episodes are sponsored by the listeners on Patreon. So you can go to patreon.com/Sean M. Carroll, and you can support Mindscape with $1 or $2 per episode. It's fine if you don't, but it's nice if you do. And then you get to be part of the community. You get ad-free versions of the podcast, and you get to ask these questions that we are here answering on the AMAs. Too many of them for me to answer all of them, but I try to answer ones where I have something interesting to say. And with that, let's go. First question is from Rue Phillips. I'm actually continuing the climate change thread here, so I picked Rue's question to go first, just to keep that notion in your head. So Rue asks the following: I am trying to understand the science of climate change, the potential harm, and what can be done about it. To do this, I read books, watch the news, read summaries of climate reports, etc. So when I come across a book like Unsettled by Stephen Koonin, I am left wondering, is climate change politicized and sensationalized enough that it will never be realistically understood enough by the layperson voter? I would summarize the main takeaway of Koonin's book as a need for us to be more careful about what the science says, and in particular with what uncertainty, and not broadcast headlines that are far from what the data really say. How do we get voters better informed on climate change without ulterior motives? Well, there's a lot going on here in this question. I will try to answer it in as level-headed a way as I can. There is a very broad consensus by a very wide spectrum of experts in climate change, people who actually study the atmosphere and the earth for a living, that number one, the climate is changing very rapidly. Number two, it is mostly due to human activities one way or another. And number three, the consequences of this will be disastrous. There's also a large number of people who are highly resourced and motivated who don't want us to do anything about it, or not anything that might, for example, hurt the pocketbooks of the oil industry, the fossil fuel industry more generally. So you have scientists who, of course, scientists don't always agree with each other. Of course, there are uncertainties. Of course, it's very difficult to model the climate. Climate science is endlessly fascinating and complicated. The climate is a complex system. It's very, very hard to say exactly what's going to happen. It's going to be very hard to make accurate predictions, but the data are crystal clear. And in fact, over the last 20 years, whenever climate scientists have gotten together to make projections about what will be happening to the global climate in the next 20 years, they have underestimated very, very consistently what the size of the effects are actually going to be. The climate has been changing noticeably more rapidly than climate scientists worried about. So yes, there is uncertainty. Yes, there is unsettlement. But no, there is not a feeling that somehow it's being sensationalized and alarmized so that people are more worried than they should be. People are less worried than they should be, is the truth of the matter. And I'm not sure how it's possible to miss that conclusion if one does actually read summaries of climate reports and look very carefully at scientific work by experts in the field. Stephen Koonin is someone who I know of. He used to be a Caltech professor before my time. He's a physicist, and he's known not so much for contributions to physics, but for administrative things. You know, he was the provost of Caltech. He worked for government for a while. He also worked for the petroleum industry for a while. He was chief scientist at British Petroleum. And so he's not only not a climate scientist, he is exactly the kind of person who is a mouthpiece for making people feel that climate change is less of a worry than it really is. I just did 2 minutes of Googling before doing the AMA, and I found the following quote by Koonin: "The impact today of human activity appears to be comparable to the intrinsic natural variability of the climate system itself." Not to put too technical of a spin on this, but that is complete horseshit. That is very, very wrong, as any actual climate scientist will tell you. So yes, I absolutely think that we should be careful about what the science says. We should be particular with uncertainty and not broadcast headlines that are far from the data, what the data really say, and also not pay too much attention to people with obvious ulterior motives like Stephen Koonin, who is not a climate scientist, once again. Science is hard. You know, we're not going to get the once and for all perfect answer. It's not that someone knows exactly what the climate's going to be doing over the course of the next 50 years, and as long as we listen to that one person, we'll be fine. Scientists disagree with each other. They have difficulty modeling very complex systems. So we do the best we can. The answer to uncertainty and unsettledness is not to say, well, you know, don't be too alarmist, don't move too quickly. We are taking a sledgehammer to the planet on which we live. And it's always possible that the sledgehammer will actually miraculously fix something that we had broken in the planet. You never know. You could say the same thing about taking a sledgehammer to your computer. There's a chance it will fix it. But that's not the way to bet. The way to bet with the climate is we are obviously doing terrible things to it, and we should move as quickly as possible to stop doing those things. Colleen Edwards says, "Within the last 2 years, I've become really interested in quantum mechanics and physics." Good for you, Colleen. Those are good things to be interested in. "I'm 37 and in a sales career I love, but have a basic math and science background, so the abstract equations and info associated with quantum physics can get very tricky or impossible to follow for me. That's okay, though. I like a challenge. I've been listening to many of your books and books by other fellow physicists, in addition to YouTubing and Googling the crap out of every piece of info I don't understand, in an effort to really give it an honest try, because it is truly fascinating stuff. Do you have any techniques or suggestions for helping the average Jane get a firm understanding of quantum physics in her spare time?" This is both a super important question and a super difficult question, because I feel I can say things, but they're nothing other than, platitudes. That's like the obvious things. I don't have any secrets, in other words, okay? I don't have any like, oh, if you do this, suddenly you will understand quantum mechanics really well. I think that the only thing I will say is that there are levels of understanding, and it's important to appreciate that. So if you read a popular book on quantum mechanics, like my book, for example, Something Deeply Hidden, you will be challenged because the ideas and the concepts are very, very hard. But even if you really understand it, even if it's very, very clear and you really feel you're getting something, you're never getting the full thing because you don't have the equations, okay? That's why I'm currently working on this series of books, The Biggest Ideas in the Universe, where I do the equations. I mean, I should be finishing book 2 right now, but I'm pretty close. I'm getting there. Don't worry. And I also did YouTube videos with the same title, The Biggest Ideas in the Universe, where you can find some of the equations there. And then you can be very serious. You can look at textbooks, or you can go to online courses from places like Stanford, MIT, and elsewhere, where they really do the details of quantum mechanics. And there's no right or wrong here. There's no correct level of understanding. Different people learn in different ways. Some people like books, some people like videos, some people like talking it through. If you really want to understand it, you have to do problem sets. You have to solve some equations and play around, Playing and creativity and experimentation are crucial to really taking some of these difficult ideas and making them embedded in your bones. But most people, they don't have the time for that, much less the inclination. So, you will never be satisfied then. But that's okay, is my message. You will never think, oh, okay, now I perfectly understand quantum mechanics. I hope you never feel that. I hope no one in the world feels that. When I wrote a op-ed for the New York Times a few years ago after publishing Something Deeply Hidden, and I said, physicists still don't understand quantum mechanics, and what is even worse, they don't even try. Almost all of my physics colleagues who emailed me about that loved it. They said, oh, yes, this is great. I'm glad you're speaking up about this. There was only one person, I'm not going to say who it was, one person did email to say, well, I understand quantum mechanics. I don't see what the problem is. Most people get that all of these things are very, very difficult to master. So the platitude I would offer is enjoy the journey. It's not about the destination. Find which modalities work for you, whether it's YouTube or books or just talking to physicists on Twitter or whatever, and enjoy understanding a little bit better every day. 1% better every day is the motto of Tyrese Maxey, who is one of my favorite Sixers basketball players. If you can understand quantum mechanics 1% better every day, you'll be on the right track. Mike Brock says, as a social species, it seems that through language and technology, humans have become part of an emergent information processing superstructure, with the internet, AI, and complex societal systems as additional rungs above us. In the past, individual choices had a more significant impact on society's trajectory, but now it appears that these emergent systems are the dominant forces shaping our collective destiny. As an advocate of poetic naturalism, how do you perceive this potentially darker view of the diminishing importance of the self and the sense that humanity's age may already be over, with society's coordination increasingly beyond human control? As a follow-up point in question, I worry that all this has grave implications for the stability of democracy. Given your research into the physics of democracy and your personal appropriation for you wrote appropriation, Mike, but maybe you mean appreciation, for democratic systems of government that I share, what do you think of these concerns? I'm not sure what answer you're anticipating here, but my answer is I completely share these concerns. I think these are very, very important concerns. So to rephrase it a little bit, just to make sure that I understand, the world is changing. Technology is changing the world. The world is shrinking, right? We're more in contact with people around the world. Global events can affect us and affect us quickly in ways maybe they couldn't 200 years ago. And also as a result of that, because you can sort of influence and know about larger and larger swaths of the world, it is possible for nations and international systems to become bigger and bigger. There are inefficiencies in the economy or whatever that go away once everyone is connected to everyone else. That's the good news, but the bad news is there's also systems of control that become much, much larger than individual human beings. And I think that the worry about democracy is very much on point, because a typical person, let's say in the United States, where I live and I'm most familiar with, a typical individual doesn't think they have much say in the federal government, right? Probably not even in the state government. There's this idea that there's this giant system that has an enormous impact on our lives, and we have very little say in it. Even if it's a democracy, you're still one out of hundreds of millions of people. And when you look at what politicians are doing, what government is doing, et cetera, it is very easy to get the impression that they're not centrally focused on the concerns that are uppermost in your own mind. Couple that with the fact that there's a lot of things to couple it with. Two things. Let me just mention two things. One is that because the world is changing, you can have situations where your family was involved in some industry or some job for generations, and now that job is disappearing. So you can't do it anymore. There's disruption. Maybe you lived in the same house for a long time, but there's some reason why now you have to move. So there's disruption there. So there's this feeling that the expectations that we have of what life is supposed to be like are declining over time. We don't have the ability to just sort of stay the course. There's no like happy medium where we just do the right thing, act like good citizens, and everything is fine. It's become more effort to find a niche where we can individually be successful. That's one consideration. And the other consideration is that the elites, if I can put it that way, people who are either captains of industry or what have you, or people who are in the government, et cetera, are getting better and better at manipulating the levers of control, right? It's, if you have a local coffee shop and it's really just that one coffee shop, it's not a member of Starbucks or whatever. And I'm trying to say this in the least weird, scary, conspiratorial way. But if there's literally a local store that is owned by people who work in the store, you go into it, something is wrong, you can complain. And you're complaining to the owner of the store who has a vested interest in making it better. If you go into a franchise of a huge chain and you complain, you're just giving a hard time to some poor person who works there. You're not talking to the owners, to the real people who have control over what is going on. So once again, it is hard to have an impact in many institutions that are very, very important for your individual life. What to do about this, I'm not sure. So I don't know what to say about Mike's question here. I think that there is a problem. I think that there's a problem that has been understudied, as far as I know, just dealing with the scale of modern institutions versus the concerns of the individual. And I worry that that mismatch that has grown up in the recent decades does have deleterious effects on democracy, especially people's interest in preserving democracy. Why preserve democracy if your vote isn't changing anything, right? I think that's a very, very real worry. And we see it, by the way, in the rise of populism and romantic nationalists, because people just get frustrated. And so rather than voting for someone who is a sensible person who will implement good policies, they vote for people who they think will shake things up. People who are not beholden to the usual ways of doing things or whatever. And, most ways of shaking things up make things worse rather than better. A lot of them appeal to our less good instincts within ourselves. So these are all problematic things we have to worry about. Walter E. Miller says, in discussions about antimatter, the first consideration is usually, why did all the antimatter from the Big Bang disappear, leaving us in a matter-only universe? If that's true, why is it that antimatter pops up so often in our matter-only universe during radioactive decay? One example is neutron decay that includes an antineutrino. Rather than being an interloper, is antimatter actually an embedded fixture of our so-called matter-only universe? Well, if you listen to scientists talk about the asymmetry of matter and antimatter, there's different levels of carefulness that they will sometimes tell you, including myself here. I'm not excluding myself from this very, very mild critique. Sometimes they will say, there is more matter than antimatter. Why is that? The truth is, we don't know. if there is more matter than antimatter, because many of the particles, in fact, the vast majority of particles that make up the known universe are either photons, which are sort of their own antiparticles, so they're even, or neutrinos. Neutrinos are very low mass particles that were created in abundance in the early universe. And we have very little, if any, idea whether that neutrino background in cosmology is mostly neutrinos or antineutrinos. We don't even know. It's just very, very hard to measure. We can't detect it directly. So if we're being a little more careful, we say that what really clearly exists in the universe is a baryon asymmetry. Baryons are the heavy, strongly interacting particles like protons and neutrons. And there we know that in our observable universe, there are far more protons and neutrons than antiprotons and antineutrons. And that by itself is a puzzle. So the scientific challenge is baryogenesis. What created the asymmetry between baryons and antibaryons? Maybe there is a compensating asymmetry in the neutrino background that gives us more antineutrinos than neutrinos, or maybe not. We just don't know. But, antimatter is not anything weird and scary and difficult to make. Like you say, Walter, antimatter is produced all the time. Okay, the Large Hadron Collider at CERN collides two protons together, but the Tevatron at Fermilab collided protons with antiprotons. The reason why the LHC doesn't do that is because antiprotons are much harder to make, and the LHC is trying to have a large luminosity, as many collisions as they can possibly get. So it's just easier to make protons and protons rather than depend on your supply of antiprotons. But anyway, the point is that antimatter is by no means itself mysterious. Why there are more baryons, protons and neutrons, than antibaryons, that is mysterious. Rob and Jess ask, a fact that gets thrown around a lot in pop science books is that light, because of its speed, doesn't experience time. But if a photon doesn't experience time, if the universe is frozen for it, then what happens to it when time passes and the universe changes? Surely the photon then must experience some type of time because the universe it exists in has changed and time is change. Well, number one, I wouldn't say time is change. I don't think it's quite that simple. That's like a little motto that has some validity to it, but not 100% validity. But more importantly, I'm developing, this is a question I get many times. I've talked about it many times. I'm developing a slightly new take on this question because this is a question where the equations are 100% clear. Right? I mean, there's no actual issue in writing down what is happening for photons. The correct thing to say about a photon, as long as that photon is moving freely through the universe, not bumping into anything else, then it's elapsed proper time, as we define it in general relativity, its elapsed proper time is zero. That is true for any massless particle. Now, for you and me, what the proper time is the amount of time we experience, the amount of time that is read on our wristwatches, okay? Any clock we bring with us measures the amount of proper time we experience. For a photon, that number is zero. But, as you say, the photon is moving through the universe, which is changing what is going on. I think that there's a major problem that people have because they want to imagine what it must be like to be a photon. What would it be like? Literally, Einstein imagined this. What would it be like if we were moving at the speed of light? But the thing is, if you were moving at the speed of light, the thing is you're not moving at the speed of light and you can't, okay? Individual massless particles can move at the speed of light. As soon as you get more than one particle together in a system, it will generally have a mass. It will generally have a non-zero energy density in its rest frame, and therefore there must be a rest frame, and therefore it's not moving at the speed of light. You can have two photons moving at the speed of light, but they're not connected to each other by a string or anything. They're just moving, on their separate trajectories. So the idea of experiencing time just isn't relevant to a photon. It doesn't have any memories. It doesn't have any experiences, okay? And this is, you might think that this is kind of a beside the point kind of observation, but I think it's very relevant to clearing up our internal worries about what is going on here. An electron doesn't experience time either, because an electron doesn't have a clock that it's carrying around. It does have a proper time that we can measure, but it doesn't feel anything. It doesn't see what's going on in the universe. I think that's the fundamental issue. We have this issue that if we were moving close to the speed of light or at the speed of light, what would we see and experience about the universe around us? But there are no things that move at the speed of light that had any experiences whatsoever. So just say the true thing would be my advice. The true thing is that the proper time elapsed on a photon trajectory is 0. And there's no clocks moving at the speed of light, so that's not a worry for what clocks think or what changes or anything like that. It is both true that the photon exists at different moments of time as measured in the universe, and that 0 proper time elapses along its trajectory. Astro Nobel says, will the quantum computer help to determine which of the 10 to the 500 possible string theory models fits best to the universe we live in? Short answer is probably not. At least I don't see any special way that's going to happen. The problem is we don't have anything like a list or even a characterization of those 10 to the 500 possible string theory models. For one thing, the number 10 to the 500 is wildly hand-wavy. Some people think it's much smaller than that. Some people think it's much bigger than that. Some people think the whole conversation is just kind of nonsense. Okay, 10 to the 500 came up, I think, probably in this paper by Raphael Busso, previous Mindscape guest, and Joseph Polchinski, where they first started thinking about what we now call the string theory landscape, different ways to wrap branes and fluxes around extra dimensions to give us different low-energy laws of physics. They estimated a number something like that, but it's just an estimate. We don't have a list. We don't have a definitive way or an algorithm for constructing all of these things and saying what they are. So there's no list to search through for a quantum computer, okay? Maybe the quantum computer can help us solve the equations that will produce such a list. But then it would have to do a lot of work to predict what a particular configuration of extra dimensions implied for low-energy laws of physics. It seems impractical to me, even for a pretty big quantum computer, but I've been surprised before. Dutch Cheese says, do you understand what is meant by reincarnation? I have been listening to some podcasts about Buddhist philosophy, but there seems to be no self. Everything is interdependent. There is just experience. There seems nothing personal left to reincarnate. I don't understand this paradox. So I'm probably the worst person to ask about this question, because I think that there is no such thing as reincarnation. Therefore, I don't need to know what is meant by it. Buddhist philosophy is an interesting thing. There's a lot of good stuff going on there. But the same thing is true for other philosophies. There's a lot of good stuff going on there too. What is not going on in Buddhist philosophy or Native American philosophy or Anglo philosophy or German philosophy or anywhere else from centuries ago is a modern understanding of physics, especially quantum mechanics, okay? They may use some words in any one of those schools of thought that kind of roughly corresponds, almost by coincidence, to an idea in modern physics, but that was not based on data and the Schrödinger equation or quantum entanglement or anything like that, okay? So from the point of view of modern physics, there is stuff, and the stuff is described by the Schrödinger equation and the rules of quantum mechanics, and that stuff comes together under the right circumstances to make a person as a higher level emergent phenomenon. And so you are made out of the stuff that you are made out of. There's no extra stuff other than the physical stuff that makes you up. And so I've given talks and written things, blog posts anyway, about life after death according to modern physics. You could Google them. It's pretty easy to find. And I'm very clear about the fact that when you die, the process that is you ends. The atoms that make up your body are changed very little, if at all, upon the moment of death, but the process changes a lot. Like snuffing out a candle, okay? The candle doesn't change that much when you snuff it out, but the flame stops. And gradually, after you die, the arrangement of atoms in your body that gave you who you are, your memories, your personalities, your ways of living in the world, all that decays, all that ceases. There ceases to be connections between neurons and so forth. So there's no sense in modern physics in which anything like the traditional notion of reincarnation has any plausibility whatsoever. So I would say that, and let your favorite philosopher or theologian deal with it as they will. Dan Jaglowski says, what happens when antimatter falls into a black hole? Are there antimatter black holes? If so, what happens when an antimatter black hole collides with a regular black hole? So you can make a black hole out of antimatter, but, well, if you had enough antimatter, you could hypothetically do it. You never will have that much antimatter, but you could. If you did, though, it would not be an antimatter black hole. All black holes are described by their mass, the total energy in other words, their electrical charge, and their spin, their angular momentum. So that's all. That's all the information that tells you what your black hole is. In particular, the information about whether or not it was made of antimatter or matter originally is not included in what characterizes a real-world black hole. So there's no such thing as an antimatter black hole. There are just black holes. You have to think black holes are not objects like rocks or stars or brown dwarfs or anything. They're regions of space-time. Black holes are made of space-time. That matter that went into making the black hole goes behind the event horizon and is now lost to us. So what happens when an antimatter black hole collides with a regular black hole is exactly what happens when any other two black holes collide. You get a bigger black hole. Johann Falk says, I'm trying to make up my mind about how to treat the risk that humanity is overrun by artificial general intelligence within, say, 50 years. And I find myself in a situation similar to Pascal's wager or Pascal's mugging. A non-negligible fraction of AI researchers think that there is at least a 10% risk of human extinction or similarly permanent and severe disempowerment from future AI systems. How do you think that I or people in general should treat risks like this? Well, I think you should treat them cautiously. I think that people in general should be cautious when it comes to AI, but not be alarmist. I think there's a difference between those things. I'm not sure what is going through the minds of a non-negligible fraction of AI researchers who think there's at least a 10% risk of human extinction. After all, these are people who are experts in AI. They're not necessarily, by the way, I'm not even sure they are experts in AI. Some people are kind of self-proclaimed experts in AI, even though they've never written a backward propagation subroutine for a large language model or anything like that. But anyway, being an expert in AI is very different than being an expert in human extinction. Being an expert in biology and sociology and economics and ecology and whatever it might take, right? So I don't take these estimates very seriously at all. But that's okay. I think that unlike the climate change situation where we kind of know what's happening and it is definitely bad, in the AI situation, we should recognize the unknown. That is to say, we're doing a new kind of thing. That's the interesting thing. The interesting thing is not we're doing a dangerous thing. We're doing a new kind of thing. And we should always be cautious when we do something radically new like that. I always think back to Martin Rees, who was on the podcast, and we were talking about existential risks from the Large Hadron Collider. And he made a really, really good point. He said, he was testifying before some parliamentary committee or whatever, and he said, there absolutely, as being a good scientist, right? He said, look, there absolutely is a non-zero risk that the Large Hadron Collider leads to something disastrous, ending the Earth or whatever, something equally bad, okay? He said there's also a non-negligible chance that the Large Hadron Collider creates a panacea, creates free energy, shows us how to, violate the law of conservation of energy and gives us, removes us from our need for fossil fuels or anything like that and makes humanity awash in abundance. Both of these possibilities are very, very, very tiny. One of them could be literally 1,000,000 times bigger than the other, and we just don't know. So what do you do? How do you balance these things? And I don't think that human beings are very good at balancing these very small probabilities versus huge impact kind of events. So therefore, rather than, trying our best to pretend to calculate a number and attach it to the probability of something very bad going wrong, we should just be cautious, right? I mean, we should just move slowly. We should be careful about checking what we're doing. We should try to think of all the specific ways that things could go wrong. So I'm just not interested when people say, I think there's a 10% chance of human extinction. What does that mean? Where did that number come from? How do you calculate that? If you say, here is a path for human extinction, that gets me much more interested. If this happens and then this happens and then this happens, it could lead to terrible consequences. That's a useful contribution there when you say things like that. And you have to be very, very specific, very, very clear, right? You can't just say, well, it's very powerful. It can do things. You need to be much more clear about that, because only then will you enable us to do something constructive to prevent that from happening. I don't think that the call for a pause in AI research is a very good idea, if only for practical reasons. Like, no one's going to get everyone in the world to pause all their research. In fact, there was for those of you who don't know, there was an open letter calling for a 6-month pause in AI research. And some big names signed it. Some of those big names are still going great guns at AI research, trying to outcompete their competitors, okay? So it's just practically very, very hard to do. I mean, it's kind of a symbolic action that makes you feel good without actually changing anything. I'm much more interested in figuring out what are the pathways for AI to actually do bad things, and then try to figure out how to prevent those pathways from coming true. Craig Stevens says, my understanding is that one of the first demonstrations of the superiority of Einstein's theory of general relativity was that it correctly predicted the orbit of Mercury, which Newton's theory did not. If this is true, what is it about Mercury that makes Newton's laws of motion fail in this instance while working perfectly well elsewhere in the solar system? I like this question because I know the answer to it. It's very specific and definite. Two things, actually, that are both required. One is, as you said in a parenthesis I didn't read, Mercury is close to the sun. The gravitational field that Mercury is moving in is just a little bit stronger than the gravitational field that Venus or the Earth or whatever moves in. If you go through the equations, there is a correction to the Newtonian equations of motion that comes in general relativity, that comes in more and more noticeably the closer you get to the sun. Very, very roughly, I don't want to push this too much, but very roughly, if you think of Newtonian gravity as 1 over r squared, right, the famous inverse square law, there's a new contribution in general relativity that goes as 1 over r cubed. So when r is large, 1 over r cubed is negligibly small compared to 1 over r squared, but when r gets small, then you begin to notice. The other thing that is equally important is that Mercury has an eccentric orbit, okay? It's not in a circle. If you had a perfectly circular orbit, or even a very close to circular orbit, then the amount of precession you would get is both less and harder to measure. So we got lucky with Mercury. I mean, we really got lucky when you think about it. It was just the right distance and just the right eccentricity to be noticeable by 19th century astronomers, so that it was there for Einstein to make that prediction. Sandro Stuckey says, as an author, podcaster, and generally someone who makes his voice heard in public, do you ever get criticisms or negative reactions that feel distressing? And if so, how do you cope with that? Also, to balance the question, what kind of positive feedback do you most enjoy? I mean, yeah, I get negative reactions all the time. There's a huge selection effect in people reacting to things on the internet that favors negative reactions, right? People, like, many times, whether it's on Twitter or YouTube or blog comments or whatever, I just look at it and I say, like, why did you bother to leave that comment? It's often not, here's a substantive criticism that I have of you, but just like, well, I listened to you for an hour and it was really boring. I didn't learn anything. So, okay, so but why do you listen for an hour? And furthermore, why did you feel like you need to spend extra effort to go leave a comment? It's a little depressing. I'm not a confrontational positive kind of guy. I'm a confrontation avoidant kind of guy. And it's the single biggest downside of having a public voice on the internet and elsewhere is that you constantly get criticized. And also, I'm not blameless myself. I'm working very hard. I'm not very good at it, to be more constructive and less snarky on Twitter and on the internet more generally. more productive, more pushing positive agendas of constructive ways to live in the world rather than just making fun of people I disagree with. If you look at Twitter these days, or ever, not just these days, but it's just so easy to make fun of people. That's what people just do back and forth all the time. And I get it sometimes. And I don't like it. It affects me. I remember the negative comments, or it's not that I remember them. I honestly couldn't tell you what most of my negative comments were, but they have an impact in the moment on me that is much greater than the compensating positive comment. So I do like positive feedback, but I also like critical feedback that is actually constructive, right? Like saying, well, you did this, but maybe you should say this instead. Like, that's fine. I love that. But that is very, very rare in our modern internet. Redman says, infinity is a mathematical concept, not a number. We haven't encountered infinity, and even if we did, we would be unable to measure or count it. Why, then, is it practical, important, or even meaningful to describe space-time as infinite in extent, as opposed to immeasurable? Well, because it might be infinite in extent. I mean, this is just how science works. We make hypotheses. We compare them to the data, right? So that space-time is infinite in extent is a hypothesis. If you simplify your life and say that space-time is either infinite or finite, that matters, right? You have different theoretical ways of dealing with that. I mean, let's think about time in particular, because it's a little bit more vivid there. If you just use the ordinary equations that we know and love of quantum mechanics, time doesn't end. There's no beginning, okay? In the usual Schrodinger equation, starting from any wave function, I can evolve it forward or backward an infinite amount. So my theory, like I didn't develop the Schrodinger equation. I didn't develop it at all, but Mr. Schrodinger didn't develop it to understand the Big Bang. He was thinking about atomic spectra and things like that. But what we do in science is we take the theories that work and we extend them beyond where we develop them. And we say, is it still working? We don't assume that it does work, but we presume that it is applicable, and then we test it. We go and look for whether or not the predictions that are made using that method make sense. So if you think that the universe had a beginning, if you think that time is not infinite, or likewise, if it is not infinite to the future because it has an ending, tell me where that shows up in your equations, okay? You need to work to explain how that appears, and maybe it does, but you're trying to understand the world at a deep level, and if that is made easier by postulating a space-time that is infinite in extent, then good. Then you should do that, and you should put high credence on that being true. By the way, parenthetically, we don't have such high credence right now. I mean, people describe space-time as possibly being infinite, but honestly, we don't know. We can't see it. We don't know enough to say right now, so you shouldn't be too confident about those things. Jeremy Merrill says, nuclear proliferation is much more common in the last 70 years than states giving up nuclear weapons, since having nuclear weapons confers benefits to those who possess them, mainly not being attacked by other countries, and the technology needed to develop nuclear weapons becomes more accessible over time. Doesn't this trend lead inevitably toward nuclear war at some point in the future? It's hard for me to see how it could not. Well, not inevitably, no. I mean, I think that putting the word inevitably in there weakens your argument immeasurably, because inevitably means there's a probability of 1. Maybe the probability is 0.999, but someone's going to nitpick you on the word inevitably. The relevant question is, does it make nuclear war more and more likely to the point where it becomes probable, or in any case, something we should really worry about? If nuclear war is only a 5% chance of happening, I think that's something we should very, very much worry about. And there, I think the answer is yes. I mean, I absolutely am extremely worried about nuclear proliferation. There's more things that can go wrong when more people have access to incredibly destructive technologies, right? I'm not sure what to do about it. I mean, ultimately what to do about it is to make the world a better place. Spread democracy and prosperity through the world so that no one wants to start a nuclear war. I mean, the United States is not going to attack Canada with nuclear weapons because there's no benefit to doing that. We want to make every country in the world like that. And then, I can imagine a future where countries do voluntarily give up nuclear weapons. Right now, it seems very unlikely for exactly the reason you say. It gives you leverage. It gives you a voice at the table. If you have nuclear weapons, you can't be ignored, okay? So one of the reasons why a lot of people give for either supporting Russia or at least not supporting Ukraine in their recent war of Russia invading Ukraine is that Russia has nuclear weapons. We don't want to get them too angry so they use the nuclear weapons. Therefore, we should mollify them in some way. It's kind of analogous to the, LHC, AI, existential risk thing, because are you sure that by mollifying Russia or any other nuclear power, you're not making nuclear war more likely rather than less likely? This is very difficult to know. It would be much better if we could just decrease the number of countries that had nuclear weapons. That's beyond my pay grade to see actually how to do that. But I do think, let's say this. We don't talk about nuclear war these days nearly as much as we did when I was growing up, right, in the 70s and 80s. There were real worries. It was the Cold War, and there was real worries we could actually have a nuclear war. And since the Cold War ended, even though there are still lots of nuclear weapons out there and lots of countries that have them, it is less high on the list of global concerns. And I think that is a problem. I think that's too bad. I think we should worry more about nuclear war via proliferation than we actually do. Shambles says, somewhere over 40% of people are now categorized as neurodivergent in some way. That number is still going to increase as we understand more in the relevant fields of study. Do you feel these labels are useful, as they will likely cover half of humanity fairly soon, or should we be looking to dispense with them and reassess what the heck is normal anyway? Well, I don't have a specific recommendation for whether or not that label is useful or we should do something else. But let me talk about this general issue, because I think it is actually crucially important. The way that I see it, what's happening is that in the modern world, we are gaining at the social level, not at the individual level, more understanding and more respect for differences between different kinds of human beings, not just neurodivergence, although that's one way of doing it, but gender and sexuality diversity is another very obvious kind of thing. Ethnic racial diversity and, who belongs in what category and so forth. We're becoming a little bit more careful and nuanced and hopefully a little bit more humane in dealing with these kinds of questions. It's just easier to ignore differences, to categorize people as our people and everyone else, to give our people the rights and take them away from other people. I think that as a society, we're trying to do a little bit better at that. And I think that's good that we're trying to do a little bit better at that. As I'm sure as you're thinking right now, it's not universal that we're trying to do better at it. Some people are trying to drag us back to the Stone Age. But I do think that, we're getting a little bit better, and that's a good thing. But it's also hard. It's not a straight line. People make jokes about the name that we give to Black people in the United States. Is it Black people? Is it colored people? Is it African Americans, right? Negroes? What is the right word to use if we're trying to be as polite and considerate as possible? Right? Even if your goals, your intentions are as good as they can be, it's still not clear what you should actually do. My point is just that that's okay. That's what you should expect. These are hard questions. You shouldn't say, well, if we don't get it right immediately, then somehow there was something wrong about the attempt. People will work this out. Neurodivergence is something that I'm very glad that people are recognizing the existence of it and thinking in a more careful way about how to deal with it. We had the podcast with Camilla Pang, who talks about exactly this as a neurodivergent person herself. And it's hard, right? It's not like, okay, I'll be polite, therefore everything I do is going to be okay. Right? You need to actually think about what it means to live in a world where people are kind of complicated. It's easier to live in a world where people are simple and those who diverge from the simple expectations are bad or wrong or, should be shunned, right? That's a much easier world to live in, but it's not a better world. So we're beginning to learn to deal with this kind of complexity and divergence. I don't know what the vocabulary is going to be 100 years from now, but as long as we try in good faith and try to respect each other as much as we can, I think that the process is going to get us to a better place. John Stout says, can you clarify what is the significance of this? Nima Arkani Hamed often begins his talks by saying this, and Leonard Susskind said, quote, put a bit of information at every point in space, and then your number of bits will be proportional to the volume. What's so hard about that? Well, what's so hard about that is you'll wind up putting so much energy into the region of space that you create a black hole. And the black hole will be bigger than the region that you were trying to populate in the first place with information. So using ideas from black holes, from Hawking and Bekenstein and so forth, I think Tuft and I both came, somewhat independently, to the conclusion that you under no circumstances could ever put more information into a region of space than its area. Area measured in little Planckian pixels. And once you say that, you begin to think, well, maybe there should be some theory in which the interior volume of a region should be described by degrees of freedom that live on the boundary. Yeah, I mean, what the significance of that is that Susskind is just describing what we call the holographic principle, right? The idea that not all points in space are independent from each other. And it's kind of a basic feature of gravity. Once you know there's gravity, once you know there are black holes, okay, which is a new thing in general relativity. There's no black holes in the same sense in Newtonian gravity. Once you know that that's true, that's kind of a new limit on how much you can do in any one region of space-time. If you didn't have gravity, and by the way, I completely agree with all this. I even wrote a paper on it saying with Ning Bao and Ashmeet Singh, we said the Hilbert space of quantum gravity is finite dimensional. Okay, it was one of these essay contest entries. And it wasn't a new argument from us, but we tried to say that one particular conclusion as clearly and forcefully as possible. And that's a way of saying that there's a new kind of cutoff on what you can do given to us by gravity. Sometimes in quantum field theory, we talk about an ultraviolet cutoff. We say at very, very short distances, we don't know what's going on, so let's cut it off. Let's imagine that our theory just does not talk about what's going on at distances smaller than some particular length scale. And you might think that only gives you a finite number of things that can happen. But of course, there's arbitrarily large distances you can talk about. So maybe you want to put an infrared cutoff also, the size of our observable universe or whatever. And then you might think if you have a largest possible scale that you can look at and a smallest possible scale, there's only a finite number of things that can happen inside. Still wrong, because at every point, an infinite number of things can happen. Not only can I put one piece of information at one point, that information can be the number 0 or the number 1 or 2 or 3, and it will eventually, in physics, cost more and more energy to excite the quantum fields that are doing that counting. And so without gravity, you can do an infinite number of things in any region of space-time. But with gravity, as Lenny says in that quote, you will just create a black hole. And if you're limited to a certain region of space, there's a biggest possible black hole you can make. And really the lesson of this, the holographic principle, et cetera, is that information is not separately distributed at regions of space. There's something that is non-local about how the world works at a deep level in quantum gravity. I don't think we're quite ready to say what exactly that is, how exactly the non-locality should be talked about in quantum gravity, but we're getting closer and closer to it. You can look back at the podcast archives for discussions we had with Lenny Susskind, with Raphael Busa, with Netta Engelhardt, and probably some other people about where this kind of non-locality comes from and what we're going to do with it. David Maxwell says, my work can sometimes be about an interesting thing, and sometimes the actual day-to-day work involves is intellectually satisfying, but it's seldom both. How much of what you do professionally, both in your higher level choices and in the day-to-day work, is for academic enjoyment, and how much is because you're passionate about a question? Did you get into physics because of a sense of wonder? Do you stay in it and expand and refocus the way you do because you enjoy the intellectual stimulation, or because you want real answers and believe you can help find them no matter what type of work is required? Is it the journey or the destination? So I'm going slowly in answering this question because when it started, I thought it was going to be something else. I'm a believer that in almost every kind of work, there are aspects of it that are interesting and fun and rewarding, and other aspects which are just tedious. If you're a professional athlete, you got to practice, you got to work out and exercise. If you're doing general relativity for a living, you have to push some tensors around, and it's never that much fun. Although general relativity itself is fascinating, being an athlete is kind of cool. Likewise, if you're a musician or a writer or whatever, there are tedious aspects of what you do. There are rewarding aspects of what you do. But David's question is not apparently about that. It's a more subtle distinction between the day-to-day progress being interesting and worthwhile versus the final product being rewarding. And that's a tougher one. I think to me, it's got to be both. I would be very unsatisfied if the day-to-day manipulations were interesting and cool, but didn't lead anywhere. I'm a believer that one wants to accomplish things in physics. I always tell my students this, by the way. This is a slightly difficult lesson to learn as a graduate student, because when you're a graduate student, in theoretical physics, very often when you were an undergraduate, you took courses, but you didn't write papers. You didn't do publishable results in theoretical physics. And now in graduate school, you are. So you have a new talent, a new capacity. You can write publishable theoretical physics papers. And I know this from my own experience, you can be so swept up in that the very fact that you can write a paper about something inspires you to do it. I can write a paper about this, let's do that. Rather than stepping back and saying, but wait a minute, I only have a finite number of heartbeats left in my lifetime. Am I writing the most interesting and important papers that I can possibly write about, as we talked about with Andy Strominger recently? That's a trickier thing to do. But so I do think it's important to aim for things that give you a destination, but you also, of course, want the journey to be interesting also. So I don't think there's any simple answers to this one. It is a good question, a subtle one. I think it's one of those questions where you balance, right? I mean, if you were a musician and you did nothing but scales all day long and didn't get to play at the end of the day, that would be tough. But you can make the journey a little bit more interesting. I do think that the journey in intellectual work is fun. I mean, there's nothing more exciting than just sitting around the coffee table with fellow scientists or philosophers or whatever and being introduced to a new idea, a new way of thinking, a new twist on something you've been worried about for a long time. But then you want to go do something with it. You want to, go make something out of it, write a paper or whatever. That's also part of what we're here to do. Eric Dovigi says, if I know something about a system, is the fact that I have knowledge about it part of that system? Do I decrease the entropy of a system by studying it, or is that a totally harebrained notion? So no, it's not a totally harebrained notion. I don't think that you change it by knowing something about it, but you might change the way that you characterize it. In fact, this question you're asking is basically exactly the question that was asked in a talk that I saw by Wayne Mervold, who is a philosopher of physics. I liked the question so much that I repeated it in a talk that I gave recently on the philosophy of quantum thermodynamics, questions or topics in the philosophy of quantum thermodynamics. It's a talk that I gave recently. It's online, and I quoted Wayne's little question. And the question is the following. Let's say you have in front of you a cup of coffee with cream in it, okay, a standard example of entropy. And you look and you can sort of macroscopically characterize where the cream is, where the coffee is, and you can, doing that, assign an entropy to the system that is in front of you, okay? The weird thing about entropy is that there's versions of it that are related to our knowledge of the system. So Wayne's question is, okay, now someone else walks up to you and says, oh, I have in my back pocket a complete list of all the atoms and molecules in that cup of coffee and exactly what they're doing right now. Perfect information. The question is, did the entropy just go down? Because you now have, in principle, maybe you didn't even look at the list, but you know it's there. If you believe the person talking to you, it is known exactly the microstate of the system. And the answer is it depends on what you mean by entropy. Okay, there's definitions of entropy where you do not change the entropy at all by knowing anything about it. There's definitions where it very much is a characteristic of your knowledge. So I think that there's a simple and sadly correct answer in this case. It depends on what you mean. It depends on what you're using the notion of entropy for. And it's very operational, by the way. You might say, well, who cares? The answer is, if you know the microstate of the system, then you can be Maxwell's demon. You can extract work from a system that is in thermal equilibrium if you know its microstate exactly. If you only know its macroscopic properties, then you can't. So it does matter. It really does matter for physics and what we do for things. But I think there's a fairly simple, straightforward way of thinking about answering this question. Paul Turek says, in your Mad Dog Everettianism paper with Ashmead Singh, you suggest that reality is represented by a vector in Hilbert space. Eddie Kemming Chen proposes instead density matrix realism. The quantum state of the universe is objective. It can be pure or impure. Is there any reason to prefer a pure state over an impure one for one's Mad Dog Everettianism? So the short answer is no. There's no real reason. For those of you who don't know what's going on here, in quantum mechanics, as hopefully you've heard me mention, there are not separate wave functions for different parts of the universe. There's only one wave function for the universe as a whole. When we think about subsystems of the universe then, if those subsystems are entangled with the rest of the world, there will generally not be something you call the wave function of the subsystem. Nevertheless, there is a way of characterizing the physical state of that subsystem. If you erase all of your knowledge that it's entangled with the rest of the world, we say that the subsystem is in a mixed state, which is defined by a mathematical thing called the density matrix or the density operator. So a mixed state is basically somewhat analogous, but not quite, to a probability distribution over possible wave functions or over possible quantum states. It's a little bit more subtle than that, but that's the basic idea. So the question is, for the universe as a whole, should we think of it in terms of a pure state, a wave function, or a density matrix? The thing is that for the thing about density matrices is there's no experimental difference, right? The whole point of having a density matrix description of a subsystem is that your predictions for things you might want to observe about that subsystem are exactly the same as if you knew its precise, if there was a precise wave function for it and you knew what that wave function was. So I'm not sure that it matters that much, but also if you do have a density matrix, you can always artificially promote it to a pure state. You can just imagine there's more to the universe, and then you can what's called purify the density matrix by imagining that your subsystem is entangled with the rest of the system that you just added to it. So again, I just don't see much of a difference. I think it's simpler for me to talk about a vector in Hilbert space, but if you want to talk about a density matrix, knock yourself out. Be my guest. Casey Mahone says, I took a few art classes in college, and the one school of thought I could never understand was minimalism. Perhaps it's because I tend to go so far in the other direction. When I create or admire art, I always gravitate toward things that are full of complexity and detail. Are you an appreciator of the minimalist style, and can you help me find it less boring? Well, I am a pluralist in art appreciation like many other things. I do think that you should appreciate what you appreciate, and both maximalism and minimalism in their different ways mean something. My own art style favorites have been evolving, I think, a little bit with time. For a long time, just regular old abstract art was my favorite, which in some sense is minimal. It's not, the level of detail you find in a great Renaissance master or something like that. But Jackson Pollock or Mark Rothko, they're not going to have a lot of tiny, small-scale details. But increasingly these days, I'm looking for some sweet spot where it's kind of abstract. It's not really, a direct representation, photorealistic or anything like that, but there's also some meaning there. There's some extra layers that mean something, that refer to something in the outside world in some clever way. That's my own personal favorite. I think as far as minimalism is concerned, I might be being unfair here, but to me, that's the kind of thing where when you talk about super duper minimalism, like, a background of a single color with like a little stripe or something like that, or a dot in the middle and nothing else. That makes sense only in the context of what is going on in art at the time and in art history, right? It's a comment on what is art, what is going on right now. And it's a useful thing. I don't want to denigrate it. It's drawing your attention to certain aspects or certain questions maybe you weren't paying attention to and so forth. But I wouldn't want to hang it in my living room, okay? Or I don't even want to spend that much time looking at it at a museum. You can sort of get the point, nod, and then move on. So I think it has a place, but it's of the moment. It's a little bit less, I don't want to say of eternal interest, because nothing is, but of super long-lasting interest than some other styles. I'm old school in that I want my art to be beautiful, and I want it to be layered enough that I can appreciate it over and over again and see more and more things all the time. Justin Wolcott says, to the best of my understanding, Hume's stance on causality suggests that our belief in cause and effect is based on experience and habit, not absolute certainty. Like the philosophy of science, which acknowledges that theories are supported or disproven by evidence rather than proven, Hume highlights the limits and uncertainty of our understanding of causality. Hypothetically, imagine there was a Laplace's devil, a super Laplace demon who had perfect knowledge of the wave function of the universe. Does Hume's stance on causality still apply to them, or can they actually speak of cause and effect at the fundamental level? Well, I think there's two things going on here. One is that Hume, I'm not an expert on Hume by any means, so I'm not going to be the one to go to if you want an exegesis of what Hume actually wrote. But I get the point of what he was trying to say, and you have to distinguish between kind of metaphysics versus epistemology, right? Like what is actually going on at the deepest level versus what we can know about what's going on at the deepest level. And I take Hume's point to be primarily, although not exclusively, an epistemological one. It's about what we can know, how we infer things about the universe. We often look at the universe and we infer cause and effect, or we infer continuity through time. Broadly speaking, we infer laws of physics, laws of nature, more generally, right? But what Hume is saying is that we're not seeing those causal relationships directly. What we see is stuff. This is, even if you grant the possibility that what we're seeing is not unvarnished, okay? We just had the talk with Andy Clark where we talk about participating in creating a controlled illusion in our perceptions, but forget about that. Imagine that you just had unmediated access to what was really going on in the world. What you see, says Hume, is what's going on in the world now, and then the next moment, and then the next moment. And it's we human beings who attribute some pattern there that we would like to call a law or a cause and effect relationship, okay? So I take it that is his point, and that's going to be true whatever the form of the actual laws of physics are, whether it's classical or quantum, whether it's stochastic or deterministic or whatever. So there's an interesting question to be had. Why does this picture of having laws of physics at all work so well? And that's a very interesting question to ask. We just had a workshop here at the Natural Philosophy Forum at Johns Hopkins talking about Barry Lower's upcoming book. Barry was a recent podcast guest. He has a new book coming out on Humeanism, about the laws of physics. And of course, we had Ned Hall on earlier who also talked about Humeanism. But as far as perfect knowledge of the wave function of the universe goes, I would say almost the opposite of what you said. That is exactly where you don't want to speak of cause and effect. But this is an entirely different question than Hume's issue, okay? And the reason here is because cause and effect are macroscopic phenomena. It's very much not, there's a sort of simple-minded thing that goes around that in quantum mechanics, there's fluctuation, so there's no causality. Forget about all that. That's nonsense, okay? There are laws of physics, the Schrodinger equation, or whatever they turn out to be. That's what matters. But the point I'm making here is not that there's randomness, therefore no cause and effect. It's that the idea of speaking the language of cause and effect doesn't apply in fundamental physics, whether it's deterministic or not. Because instead, you should speak the language of the fundamental laws of physics, F equals ma. In F equals ma, there's no cause and effect. At every single moment of time, there's a force and there's an acceleration, and they're proportional to each other. It's not that one is causing the other or anything like that. It's that kind of pattern. even when you go to relativity or quantum mechanics, that characterizes the laws of physics. Speaking the language of cause and effect only becomes important at a higher macroscopic level. David Dubrow says, what is the relationship between thermal equilibrium and black holes if they both represent regions of space with maximum entropy? Well, maximum entropy compared to what? Under what circumstances? With what constraints are all the questions you have to answer. So, for example, you know that black holes aren't really regions of maximum entropy or systems of maximum entropy because they decay into something else. They decay into Hawking radiation spreading out in all directions. And you can even calculate the entropy of that Hawking radiation. It is larger than the entropy of the black hole from which it was made. The more accurate thing to say is that a black hole is the most entropy that you can fit into one region of space of fixed given size. The Hawking radiation is spread out over a much larger distance. Likewise, when you say a system is in thermal equilibrium, compared to what, or in relationship to what? Very often you have some subsystem of the universe that is more or less isolated, but not completely, okay? And in fact, this is very, very important because you can be in a metastable equilibrium. You can be in a situation that looks like equilibrium, that looks like it's in its highest entropy state, but secretly there is another state it could be in of even higher entropy. There's just no easy way to get there, right? So if you imagine a balloon with helium in it, if you pop the balloon, the helium expands to fill the room, it mingles with the air in the room, and that's a higher entropy state. But when it's in the balloon, there's still a higher entropy state. Take it out of the balloon and spread it around the room. But it can't because there's a balloon there, okay? So just because there exists a higher entropy state doesn't mean you naturally evolve to it. In the case of a box of gas that you say is high entropy or in thermal equilibrium, usually it would be the case that if we took all that gas and squeezed it into a black hole, it would be even higher entropy. The problem is that there's not enough gravity to actually make that happen. So it's always maximum entropy compared to what or on what time scale or et cetera. You just have to worry about the footnotes and the details in these questions. Tom Kenyon says, I was born within 10 days of you, and I also have a degree in physics. My question is more related to the former. What is your earliest memory of a national or world event? I often think I remember the first moon landing, although I'm probably conflating my actual memories of Apollos 16 and 17 with later TV documentaries of Apollo 11. Yes, I think that I'm not even going to give a good answer to this question because I very much appreciate this last little bit of what you said. We are terrible at remembering past events vividly, and our very first past event, I think that if you asked 100 people in the street their first memory, almost none of them would be reliable, is what I think, because we do have similar events that come later, or we were reminded of what's going on, or so forth. I would not even presume to say what my actual first memory was. I do remember going to the voting booth with my mom, who voted for Richard Nixon. That couldn't have been 68, though. I would not have remembered that if I was just 2 years old. That must have been 72. So 6 years old. And probably I have memories even before that. I definitely have memories of watching moon landings, but I would definitely not tell you that it was Apollo 11. It seems much easier, like exactly you said, that it was something else that was written over. Trevor Morrissey says, I discovered your podcast some months back and have been working my way through your entire episode catalog, which I've greatly enjoyed. After you started lamenting the fact that you would no longer be able to answer every question asked in the monthly AMAs, I was curious if you'd be interested in a fun workaround of sorts. You could load all the unanswered questions into a sports bracket and ping the universe splitter, and use spin up or down to advance one of the questions in each matchup until you're left with a final question which you would answer. We could then claim, tongue-in-cheek of course, that all questions will be answered with the caveat that it might not be in your branch of the wave function. I'm not trying to win the lottery or anything, so don't beat me up too much, just offering a lighthearted and entertaining way to end each AMA. I completely agree. That would be fun. It's also work for me. I don't like work, or rather I have too much work doing other things. So
what I'm going to do, since you bring up the question, if anyone else wants to do this, if anyone else wants to go through the questions that I don't answer, put them in a bracket. I promise I will, and then you also have to run the random number generator, which is easy to find online, a quantum random number generator. Let me know which question it is. Next month, I will answer it. Schleier says, so after your discussion with Hugo Mercier, do you think that Caliban, my cat, opens drawers for a reason? If it's too much to say that he has a reason in his little cat brain, would you say that a reason exists somewhere, either in the universe as a physical cause, or maybe only once it is inferred in the mind of a human observer? Yeah, I think that Hugo's point is that what we call reasons are in the minds of human observers. They're not out there in the world, and they're certainly not in the minds of other animals. So, I mean, that construal depends very, very much on exactly what you mean when you say reason, okay? And where the reason is located. If I let a ball roll down a hill, is there a reason why the ball rolls down the hill? Well, in some sense, it's gravity and the laws of physics and the shape of the hill and things like that. This is a standard philosophical problem. What counts as the reason why or the cause or whatever? Hugo's point, he's using the word reason in the sense that it is something given by a human being to help account for or explain why they are doing something. So Caliban loves opening drawers. He can't explain to you why he's opening them. So it is a very simple answer to this question. No, Caliban does not open drawers for a reason. That doesn't stop me from coming up with a reason why Caliban is opening the drawers, just like it doesn't stop me from coming up with a reason why the ball's rolling down a hill, even though the ball doesn't have a reason why. It's just following the laws of physics. William Benson asks a priority question. Remember, priority questions, for those of you who are new here, every Patreon supporter gets a chance once in their life to label an AMA question priority, and then I will do my best to answer it, even if I don't like it, which I'm not saying is true about your question, William. So William's question is, I am 57, and I've noticed over the past 10 to 15 years, 10, I think I read that as 10 to the 15, but it's actually 10 to 15, a very different numerical range. Over the past 10 to 15 years, a decline in my brain's ability to store new short-term memories. New information comes into working memory, pushing out other details without transferring those to short-term memory. I would like to become someone's research subject in the hopes of understanding and slowing down this frustrating decline. Also, if any new therapies are out there, I would love to see if my condition can be reversed. I'm pretty sure I don't have dementia. If you were me, how would you go about finding researchers and studies that might be interested in considering me as a candidate to do research on? Perhaps clinical researchers you've met have told you some stories of how they have found their human subjects or vice versa. So, my apologies. I know this is a priority question, but I have no idea how to do this. Or at least whatever idea I have, it's certainly no better than yours. I would go to Google, maybe go to GPT-4 or something like that in the modern era, and just ask, how can I find studies that are going on or something like that. I have never... I do know people who are clinical researchers or psychology researchers or so forth. They're generally more academic psychologists than medical doctors or medical researchers. So I don't really know people who do researches on possible therapies, and therefore I've never really talked to them about how they go about finding subjects. I think a lot of them are at hospitals or at universities and just ask students on campus if they want to be in a study or something like that. But sometimes you see a call for people to participate in studies. I just don't have any insight whatsoever on how to go about finding it. Sorry about that. David Witch, W-I-C-H, says, what are your opinions on the role of government in areas of science and technology with significant national security interest, such as advanced machine learning, biotechnology, cryptography, and quantum computing, etc.? In the last century, we saw an example of the government putting significant resources toward the advancement of nuclear technology for the war effort. Should the government be putting significant resources toward advancing these emerging fields in the public sector at national labs and institutes? I think this is a good question because the answer is a very subtle one. There's no simple answer to this one. It depends on many of the details. For, nuclear technology for the war effort, not only did it have very obvious national security implications, but it didn't have very obvious commercial applications, right? I mean, maybe building a nuclear power plant, but that would be very expensive, not obvious that it's going to make you a lot of money. So you needed the government to do it if you wanted the research to be done at all, just like you do now with what we call many fields of basic research or fundamental research. You know, you're not going to build LIGO and detect gravitational waves to make a lot of money. That's exactly the kind of research that you need the government to step in and do it. But for something like you're mentioning, machine learning, biotechnology, cryptography, quantum computing, these are all super duper commercially exploitable. Okay, if you can do any one of these well, you could in principle make a lot of money. So the private sector has plenty of resources and motivation to do well at it. I think that for various reasons, you still want some public funded research going on in these things because you don't want all the discoveries to be proprietary. You don't want all of the important discoveries in the field of science to be done by private corporations that keep them for themselves or patent them and don't let anyone else use them. Therefore, there's a very good place for research done by professors at universities being funded by the government. But it's tricky. I mean, right now we're in a situation where with the AI rush, most of the breakthroughs are being done by private corporations. Why? Because they have the money to spend on it, hopeful to get more money back in the future. There's plenty of people at universities who are doing research on AI, and some of it is very important, but they just don't have quite the resources that you have if you work for Google or Microsoft and so forth, and therefore their large language models aren't quite as large, etc. Nevertheless, many important breakthroughs, biotechnology being an obvious case example, have been done by people at universities or national labs or research institutes. So we have to keep that sector of our research efforts thriving, in my opinion. Artem Vorostov says, my friends and I come to a conclusion that your explanation of the many worlds interpretation might be incorrect, as it contains the concepts of measurement and forking. To us, this seems like a remnant of the Copenhagen interpretation. The question is, how the idea of measurement and forking matches, I never use forking, by the way, branching is the word I use, probably you're thinking of. How does that match the simple picture that the evolution of a quantum system is merely the rotation of a unit vector in Hilbert space? Well, yeah, I mean, I've said this. I think that if you look carefully at things that I've said, you won't find that much of a difference. I've said many times that the ideas of branching and so forth are useful to human beings in exactly the same way that ideas like entropy and temperature are useful to human beings. If you were a classical statistical mechanic, you would believe that, in principle, Laplace's demon might know the position and velocity of all the atoms in a gas, but you don't. And that matters. That difference really matters. To you, the best way of talking about the gas is in terms of its temperature and pressure and entropy and so forth, but not to Laplace's demon, because all of those are approximate, coarse-grained, higher-level emergent ideas. They help us with limited knowledge and limited calculational capacity to nevertheless say something interesting. But Laplace's demon doesn't need that. Laplace's demon doesn't know what a temperature is. Laplace's demon knows what every single molecule in the world is doing. Exactly the same way, in the Everett interpretation of quantum mechanics, the fundamental description is a wave function obeying the Schrödinger equation. That's it. Full stop, period, end of story. But that doesn't help we poor, limited, cognitively bounded human beings in coming to grips with what the world actually looks like according to that picture. What the world looks like is we put a spin through an experiment and we see it either being spin up or spin down. And it's absolutely a crucial part of the scientific enterprise, matching your underlying theoretical description to what you actually observe. And so for a human being trying to understand how the world works, it's not sufficient to just say there's a wave function that obeys the Schrödinger equation. Even if that's a true statement, you also want to explain why it looks like wave functions collapse when you measure them. And the Everett interpretation has no problem doing that, but that is a absolutely important step in mapping Everett onto reality. Eric Stromquist says, in earlier AMAs, I think you said that if a question isn't answered, it's fine to re-ask in another AMA, so I will give it a try. That's certainly true, by the way. You never know what mood will strike me. Just don't try to guilt me into asking a question by asking it 20 times in a row. I find the research program you described in Something Deeply Hidden to be very interesting. The program that tries to see if the metric structure of spacetime in GR can be emergent as a consequence of entanglement relationships encoded into the Hamiltonian in the energy basis that would govern the evolution of the state vector of the universe in Hilbert space. The question is, how is the program going? Well, to be honest, it is going, but it's going slowly because I lost all my graduate students. Not lost, but I stopped taking new graduate students when I knew I was leaving Caltech, and then I picked up, and then I left, and now I have some books to write, and I'm slowly accumulating new graduate students and postdocs, etc. So it's been rather slow going, although there's still a couple papers that are percolating along behind the scenes. And that's completely natural, honestly. My way of thinking about these things is, by the way, I'm not the only person. There's other people, and their research programs are going on perfectly fine without my help. But, this is a minority interest in the larger picture of quantum gravity. We have a particular way of thinking about things that I think is very promising, but in order to get other people interested, we're going to have to do more along the lines of getting good results, getting results that constitute answers to questions that people have had for a long time. And I think we can do that, but it takes time. It's not something that goes on a month-to-month timescale. It's slower than that, even if it's going forward. Nicholas Sharosky says, as one of the consequences of the replication crisis in psychology, open science efforts have become an increasingly important aspect of the field in recent years. In addition to sharing datasets in code, not talking very well today. In addition to sharing datasets in code, pre-registration is also part of this effort to prevent bad research practices, p-hacking, file drawer problem, etc. I personally think that psychology has benefited from this crisis and has emerged stronger than ever. What is your take on open science? How common are such efforts in physics, and where do you see benefits and risks for more transparent research? I think it's kind of heterogeneous between fields. Different fields address these questions very, very differently. As one example that I think would qualify as a kind of open science, you have the preprint archive, right? Archive.org. I remember when it started, and back in the 90s, and it was started by high-energy physicists, people doing formal kind of stringy high-energy physics who were sharing preprints anyway. Paul Ginsberg and Joanne Cohn and other people suggested that we just do it on a computer. We had a new thing called the internet. Actually, it was first an email list, even before it was a web page. And some people were horrified when it became a web page. Like, I don't want to learn new technology just to get my preprints. But that is a thing where you share all your research results before they've been published, before they've been refereed and anything. Anyone can comment and so forth. The whole world can see them for free without subscribing to anything and so forth. But there's different things that are meant by open science. So in mathematics, there have been some efforts where you literally do the research in an open science kind of way. So you pose a question on a web page, and then people sort of team collaborate online to try to prove a theorem or something like that. That's very, very rare in theoretical physics. And all of the stuff about registering, so you say, but pre-registration, for those of you who don't know, is an attempt to address the question or the issue that when you do an experiment, you might get a null result, right? You might say, well, there's no effect. I didn't see any relationship between my variables. And traditionally, it would be difficult to get such a result published in a psychology journal, right? I didn't see anything. It's a hard case to make. And we have a set of numerical, quantitative characterizations of when you have seen something, a level of statistical significance that you're trying to reach. So basically, you just do a bunch of experiments waiting to see something. And then when you see something, you publish it. And when you don't, you don't. So the problem with that is if you do enough experiments, you're bound to see something just by random chance, not necessarily because there's actually something going on. So the idea of pre-registration is some way that you can say ahead of time, I'm going to do this experiment. And therefore, if everyone does that, and everyone says what the results of their experiments were, they should go a lot further to actually getting decent statistical samples of when effects were real and when they weren't. Something like that isn't nearly as practical for physics. In theoretical physics, you're not doing an experiment, you're not collecting data, okay. In experimental physics, it's very often the case that either you're a small lab doing something very, very specific, but when you find it, it's easy to tell people what it is and they can replicate it right away, or you're doing big science at a giant particle accelerator like the LHC, and there's only one LHC in the world. It's important to have two experiments at the LHC, ATLAS and CMS, so they can compare each other's data. When they found the Higgs boson, they both found it at the same time. That was a big step towards making people believe they were on the right track, but you can't do 20 different things. So I think that open science is important and useful, but the ways in which it manifests itself are going to be different for different kinds of science, and I think that makes perfect sense. That's perfectly okay. Chris Gunter says, if we discovered a particle that violated the equivalence principle, i.e. its inertial mass was not the same as its gravitational mass, how big of a disruption would that be to the core theory? Consider a scalar factor between the two, zero gravitational mass or negative gravitational mass. Can a particle such as this be modeled under GR? I think there's a couple things to say about this question. So for those of you who know, the equivalence principle goes back to Galileo in some sense, but Einstein was the one who really put his stamp on it. The equivalence being discussed is the equivalence between gravitation and acceleration. If you're in a rocket ship with a very quiet engine being accelerated at 1g, you wouldn't know the difference in that between being on a room on the Earth and being in the 1g gravitational field that we're in. Unlike being in an electromagnetic field where you could have charged particles that would move differently, everything behaves the same under gravity. So it's a universal force. That's the implication of the principle of equivalence. But I think the right way of looking at the principle of equivalence is as inspiration. It's not some deep symmetry of physics or anything like that. It helped Einstein invent the idea that space-time curvature is what gives us gravity. That's the point of the principle of equivalence. But once you have that idea, you don't really need the principle of equivalence anymore. So one implication, one very weak version of the principle of equivalence is that inertial mass is equal to gravitational mass. So again, going back to Galileo and Newton, if you look at the equation of motion, Newton's second law, F equals ma, that is the inertial mass. It's saying that there's some inertia in a body. When you put a force on it, its acceleration resists. The object resists being accelerated by an amount proportional to its mass, okay? But then there's also the gravitational mass, which is the amount of gravitational force that a body creates under Newton's theory of gravity. Those happen to be equal. Newton wondered about this. So the question is, could you violate that? Would it do violence to general relativity? The answer is yes, you can easily violate it, and no, it does not do that much violence because the principle of equivalence is not some foundational symmetry. In fact, we have theories that do exactly that. Scalar tensor theories, such as the Brons-Dicke theory. In those theories, you have an extra scalar field, which is, in some sense, breaking the relationship between the inertial mass and gravitational mass. I say in some sense because really the way to talk about it is that those are quaint, outdated notions, inertial mass and gravitational mass. At the end of the day, we have a theory defined by a Lagrangian that we vary to get equations of motion. That's what matters. If you don't know what any of those words mean, I recommend you read my book, The Biggest Ideas in the Universe, where I explain what some of them are all about. Danny Avidan says, following my previous questions a few months ago and some conversations you had here since, I was wondering if you have a definition or a notion of what constitutes a moral subject. That is, where do we mark the line between things that we have a moral responsibility for and things that we do not or have less? I don't know. That's a very good question. When I say I don't know, that's a little bit too clear. But I have a vague idea. I do not have a rigorous, a very carefully delineated set of criteria. There's certainly part of it is just being self-aware in some sense, right? Let me put a footnote here. There's an extension from individuals to species or to categories that we worry about, but let me worry about that
in a second. So it's, as far as individuals are concerned, someone is self-aware, right? Conscious, able to respond to their environment, things like that. But it's much more than that. I think that part of the linchpin is something we talked about a little bit with Janan Ismail back in the day, more recently with Adam Bully and Michael Tomasello, the ability of imagination. Right? To be a moral agent, you have to not only do certain things, but you have to be able to contemplate different possible actions that you take. For many non-human animals, they do things, right? Caliban opens his drawers. He likes doing that. Not because he's sitting there thinking, well, if I opened the drawer, then this would happen. And if I didn't, then that other thing would happen. So I, imagine different hypothetical counterfactual scenarios and decide between them. That kind of ability to imagine the future and think about it, I think, is an important part of being a moral subject. But like I said, I don't have a hard and fast set of definitions there. I think that it's important to do it. I don't want to dismiss the question. It's just not something I've put a lot of thought into. Johan Löfgren says, sometimes people describe effective field theory as a framework for reductionism, but sometimes reductionism gets a bad rap, e.g. explanations of how water behaves usually don't consider water as individual molecules. What do you think? Is there a difference between philosophy of effective field theories and reductionism? Well, this is a complicated batch of questions hidden here, so I'm not going to go into great detail. Let me just say that I don't think reductionism should get a bad rap. Usually, when you read people who say bad things about reductionism, the things that they say about reductionism are not really recognizable to people who call themselves reductionist. I don't know any reductionist who says that the best way to think about water is as individual molecules in every circumstance. When you think about the freezing point of water, you're not worried about the individual molecules. You're perfectly happy talking about the higher level immersion properties of the water. A reductionist just wants to say, and there is a more comprehensive theory than thinking of water as a liquid, solid gas with certain points of phase transitions. There's a more comprehensive theory that is just as accurate as that theory, but also valid in other regimes, like when you only have one or two water molecules going around and the notions of freezing or boiling make no sense. That microscopic, more comprehensive theory is the reductionist one, and they had better be compatible. So any macroscopic features that you have in water had better be explicable in principle in terms of the most comprehensive description you have of water. That's not a exhortation to action, saying that you should think about water that way under all circumstances. It's not even an epistemological or methodological piece of advice saying that the most useful, effective, helpful way of thinking about it is in terms of water molecules. Of course, you think about things in the language that is most appropriate to the problem that you care about in the moment. So as far as effective field theories go, I'm not exactly sure what it means when you say sometimes people describe effective field theory as a framework for reductionism. I mean, effective field theory is a framework. For those of you who don't know, the idea of effective field theory, which I will be talking about a lot in book 2 of the biggest ideas in the universe, is that you can develop a theory of the low energy parts of your quantum field theory, what we call the infrared, long wavelength, low energy parts of your quantum field theory, without knowing all the details of the ultraviolet high energy parts. So you don't need to know quantum gravity to do the standard model of particle physics. You don't need to know the standard model of particle physics to do chemistry. You don't need to know chemistry to do biology, etc. So I think that understanding how effective field theories work might help you be a reductionist, but I don't know what it means to say that it's a framework for reductionism. Sorry about that. Usually, by the way, for these kinds of questions, sometimes people say, I've always found it helpful to actually find someone saying that because it's too easy to paraphrase or oversimplify when you say sometimes people say things like this. Like, find a person who says it, and then we can talk about that. Caitlin says, like Keith, who asked a question in the March AMA, I've recently been reading about statistical physics techniques in neuroscience. In general, I've noticed that mathematical biology is pretty dominated by current and former physicists. How important is it to learn, the physics of physics before studying the physics of neuroscience or the physics of democracy?
Well, I think it's helpful for two reasons. One is that you don't know ahead of time which parts of physics are going to be useful in the study of something else, whether it's neuroscience or the atmosphere or democracy or whatever. So just studying physics for its own sake, I think, is helpful because you might realize that, oh, this thing you didn't think was very useful suddenly has an application that is kind of interesting and important. But the other thing is, to be, again, a little bit reductionist about it, as we were being in the last question, physics comes closer to being that comprehensive, underlying, microscopic description of the world than any other science does. So you can certainly study neuroscience or democracy knowing nothing about physics at all. That's fine. They are independent, autonomous subject matters that you might be interested in. But they had better be compatible with the underlying principles of physics. Usually they are, and it's just automatic. You don't have to check it, but it's another way of thinking about what is going on here. So the reason why you might want to study the physics of physics first, rather than studying neuroscience and then the physics of neuroscience, etc., is because there's an arrow that points in a certain direction. Okay? There is a physics of neuroscience. There's not that much neuroscience of physics. Neuroscience doesn't help you understand the standard model. The standard model doesn't help you understand neuroscience either, but the ideas or laws of physics, the ways that you think about physics, help you understand neuroscience in a way that the ways you think about neuroscience aren't as useful in understanding physics. So I don't think it's quite a symmetric relationship between the different subject matters. David Miluk says, is the possibility of machine consciousness, not any particular machine, but in general, something that is for you subject to a credence? If so, what evidence could lead you to updating your credence? It depends on what you mean by machine consciousness. I think that the issue here is not so much that there's a 75% chance that machines will someday be conscious, as it is that we don't know what it means to say some days machines will be conscious. My suspicion is that, I guess we never said this explicitly, but maybe it's been implicit in various episodes, there's more than one aspect to consciousness. Just like when we talked to Stuart Bartlett about the meaning of life, and he said, look, there's lots of different things that go on in a living being, and they could be independent from each other. I think there's a lot of different things going on in conscious creatures, and some of them might appear in machines before others. So, we need to do more than... Let's put it this way, and this is often a way that I think about philosophy problems. I think you can get yourself into a philosophical conundrum by taking a concept that has been very useful to you and just insisting that it's there. And it's just that we don't know what the definition of it is, and then trying to figure out what the right definition of it is, like consciousness. Maybe the question isn't what's the right definition of consciousness. Maybe there's a question that is much more operational and down to earth. What are the different aspects we have in mind when we talk about consciousness for non-machine things? And then we can think about the likelihood of them appearing in machines. But my credence is very high that essentially anything that can be done by a human being could in principle be done by machines. So I don't think that there's any barrier in principle to that. I have no strong credences for when different things are going to happen. That's a prediction that I would not be very good at making. Hugin says, what do you think is the best explanation for the Higgs getting its mass? I'm going to give you a disappointing answer here, but it'll be an illuminating answer. There's no such thing as the explanation for why the Higgs gets its mass. I know why you think there might be, because in talking about the Higgs, we very often talk about the masses of other particles like the W boson or the electron or whatever and say, the Higgs helps explain why these particles get their mass. And then you might be led to ask, well, what explains why the Higgs gets its mass, which is, 125 GeV or whatever it is? Because there's a question that is implicit in the original one to the extent that you say, do I need an explanation for why particles have mass, or can they just have it? And the thing is that if you just have a quantum field theory of ordinary fields, you don't work too hard. You don't impose certain symmetries, et cetera, particles can just have mass. Like Paul Dirac didn't need to work hard to explain the mass of the electron in the Dirac equation. He just put it in. That's all it is. The reason why we have to work so hard in the standard model of particle physics to give particles mass is because there are symmetries that naively prohibit particles from getting masses. Particles like the electron, like the gauge bosons, the W and Z bosons, etc. And nevertheless, they seem to have it. So this was a late appearing problem. It was only in the 50s and 60s, once we started to understand Yang-Mills symmetries and parity violation and things like that, that we realized it was hard to both have these kinds of fields in our theories and have these symmetries be respected or violated as the case may be. So, and then Steven Weinberg figured out that the Higgs could help explain how to reconcile those two things, the idea that these particles needed to have mass and they need to have these symmetries. So typically, if you don't have these symmetries protecting your particles from getting a mass, you don't need a Higgs or anything else. Particles can just have mass. And when it comes to the Higgs boson itself, there is no symmetry that makes the Higgs boson not have a mass. It can just have whatever mass it wants. In fact, the problem is the opposite. It can literally have whatever mass it wants. And therefore, by the philosophy of effective field theory that we were just talking about, there are ultraviolet effects that contribute to the mass of the Higgs boson, and you would expect, if you didn't work very hard, that the Higgs boson should have a very, very large mass, much larger than the mass it actually has. That's basically the hierarchy problem of particle physics. Why is the mass of the Higgs so low compared to what its natural expectation is? So that's the problem. Why does the Higgs have so little mass? Not where does it get its mass from at all? Jesse Rimler says, in the April AMA, you identified yourself as a pro-housing YIMBY, yes in my backyard, as opposed to an anti-housing NIMBY, not in my backyard. A critique of the YIMBY movement is that it is ultimately a gift to large developers. Deregulation allows them to build luxury housing for large profits. YIMBYs claim that this increased supply of any kind will bring prices down, but this, some say, is trickle-down economics all over again. An alternate path would be to advocate for regulated, affordable public housing to address the immediate concerns of homelessness and low-income housing scarcity. What do you think of these arguments? I certainly don't think that those are arguments not to be a YIMBY. I mean, YIMBYs just say build a lot of housing, and some of it will be luxury housing for large profits. Some of it won't be. Just make it easier to build housing. Even low income, non-luxury housing can still be profitable for builders. I think a lot of people who are against letting developers build apartment buildings at all just don't like the idea that anyone should be making money off of this. And I do not have that moral objection. I'm fine with people making money. The more supply you have of housing, the lower the cost is going to be. As a general rule, I don't care who makes the money. You can always tax the rich. I'm very much in favor of taxing the rich and spreading the wealth from doing that. But not letting housing be built is not the way to do that. By all means, also build regulated, affordable public housing. Do that too. But guess what? We don't have enough regulated, affordable public housing right now. And if you stop people from building new apartments, you're just making the problems worse. Philip Stickney says, thinking about moral luck, would you change aspects of our justice system when it comes to something like reckless driving versus reckless driving and hitting someone? Supposing the two situations are identical, barring one resulting in hitting someone. You know, I've thought about this. I want to say I've thought about it a lot, but that's an exaggeration. I've thought about it a little bit. The idea of moral luck is that we tend to either punish or reward people on the basis of things that happen. And you might think that's a sensible thing to do, but there's an alternative that says, well, shouldn't we publish or reward people on the basis of what could have happened given what they were doing? Right? Is there really a principled justification for giving people different punishments if they drive drunk, if they do or do not hit someone? I mean, what they did was driving drunk. That was the problematic thing. If they hit someone, that's too bad, but arguably, the punishment should be just as severe if they don't. And I do think that I get the force of this argument. I feel it. It does seem sensible to me. I think that there are practical problems. I mean, I should reveal, hidden behind the scenes here, there's always a poker analogy going on in my mind. Poker players will make fun of or criticize other players for being too results-oriented. You might think that in certain aspects of human endeavor, being results-oriented is good, right? But in poker, that means you're paying too much attention to how you did at the end of the day when the cards are revealed, and not enough attention to how you are playing. You should be process-oriented because you will always get unlucky sometimes and get lucky other times, but you can't control that. You can control what you do. So a poker player would very much appreciate this argument about moral luck. But I think in the real world, there's a practical problem. It's just hard to know that someone was doing a behavior that had a certain probability of leading to a bad outcome or something like that. I think that in some ideal world where we were Laplace's demon and we knew, even better than Laplace's demon, we knew all the counterfactual worlds where we could say, well, in this number of possible worlds, the fraction of them in which something bad happened because of your behavior was the following, right? If we could do that, then we could probably punish people or reward them on the basis of what they were doing rather than what the outcomes were. In the real world, that just seems to really open things up for abuse in all sorts of terrible ways because we're not very good at knowing exactly what the probabilities are of bad outcomes. I think that it is defensible to say that our punishments should be higher than maybe they are for things that reasonable people would agree had a large chance of leading to something bad. You know, the NBA playoffs are going on, and I'm rooting for the 76ers, of course. Their coach is Doc Rivers. There have been recent controversies over players getting ejected or suspended for different actions on the court. And, one of the things is, Doc Rivers was saying he was overall in favor of not suspending or ejecting people too quickly, because what tends to happen in the real world is that there is a provocation. One player does something to provoke the other, and then there's a retaliation. And the referees see the retaliation and punish you. They don't see the provocation. And so that person doesn't get punished. And so there's an imbalance there. How to deal with that? So there's questions here of practical reason, the real world. We don't know everything. We have to be humble in our ability to figure things out and to predict the future. That those considerations have to go in to these questions. Pete Faulkner says, having just finished reading Jim Peebles' book, Cosmology Century, and listening to your responses at the start of last month's AMA has got me thinking about how science moves forward. It's certainly nothing like the A, therefore B, hence C timeline that many assume, given the way advances tend to be popularly reported. Peebles makes clear the many dead ends and wrong turns taken over the years in the development of the modern standard cosmology, as well as the breakthroughs that were not seen as such at the time. Do you have thoughts about ideas or papers that you are aware of which may fall into either of these two categories, dead ends or unappreciated breakthroughs? Well, my only thought is the following, that people should be a little bit more forgiving of dead ends and unappreciated breakthroughs. It's easy, very easy, and if you know anything about the history of science, to come up with examples of both. When I was in graduate school and we were thinking about large-scale structure in the universe, it was well known that inflationary cosmology was a candidate for generating the tiny density perturbations that would grow into galaxies and structure today. But there was another candidate, cosmic strings. Cosmic strings could easily be formed in the early universe, and they could generate the perturbations that give rise to galaxies and structures. And honestly, up until the moment when we started seeing the temperature anisotropies in the cosmic microwave background, both of these were very viable. And I'll even be more honest. The cosmic string scenario in many ways was more robust than the inflationary scenario. You need to do less fiddling and complexifying and fine-tuning to get the right kinds of cosmic strings than you do to get the right inflationary perturbations. But you then saw the microwave background, and both theories made predictions, and the cosmic string predictions were wildly ruled out. They were not compatible with what we saw. The basic problem was that the inflationary predictions are all made very early, and they sort of evolve in lockstep ever since then, whereas the cosmic string perturbations are constantly being generated all the time, so they're qualitatively very different in what you predict for the CMB and the primordial perturbations, as we call them, one out. But I don't think it was a dead end. How did you know? How would you have known, right? It was a perfectly reasonable theory. There are also unappreciated breakthroughs. We already mentioned Steven Weinberg in 1967 showing that you could explain the mass of the particles in the Standard Model, what we now call the Standard Model, with the Higgs boson. He wrote that paper in 1967 and nobody noticed. Nobody cared. Even Weinberg himself didn't cite his own paper for the next 5 years until it was 't Hooft and Veltman who showed that the theory was renormalizable, and then suddenly now it's the most cited paper in the history of theoretical physics or something like that. So those things can happen all the time. So my only grand statement about those things is that live with it. In fact, expect it, anticipate it. You can't say, well, this theory didn't work, therefore we shouldn't have thought about it at the time, unless you can give a principled reason that would have been available to the people at the time, then they weren't doing anything wrong. And, even that is hard because it's too easy to wait until we know the answer and then go, oh, yes, I know that should have been the answer all along. I can give you the following reasons why, blah, blah, blah. It's hard. That's why you have to treat science as an ongoing, messy back and forth between different people with different ideas, different styles, different predilections, etc., and see what comes out. What's important is that you let different ideas go forward. You don't decide too early that only one way of doing things is the right way, and that you are open to listening to people pursuing different ideas, giving their sales pitches for their favorite ideas, and seeing what comes out at the end. Jason Ricciardi says, what are the most impactful positives and negatives of the Future of Life Institute's call on all AI labs to immediately pause for at least 6 months the training of AI systems more powerful than GPT-4? And what would an idealized real-world rollout look like across the globe? So I think I already answered this early by accident. I probably had vaguely remembered that Jason had asked this question. I don't think it's a good idea. It's a practical matter. Okay, I'm very much sympathetic with the idea that we should be cautious, that we should be careful, that we should really think about what we're doing here. We're unleashing something. What is it? How are we going to put it to work? We absolutely have to do that. As a practical, down-to-earth person, the idea that we sort of politely ask different labs that are competing for money and first mover advantages to just stop for 6 months, that just sounds hopeless to me. So I don't think that's the right way to go. I have no idea what the right way actually is. Alexandra Marcotte says, taking into account the fact that it requires millions of years to complete a full rotation, how do we evaluate the impact of dark matter on the rotational velocity of galaxies? Well, you have already answered your question. It's the rotational velocity that matters, not the time it takes to go around the whole thing. It's true that it takes a long time for stars to complete a full orbit around the outside of a galaxy, but you don't need to follow them for a full orbit. You just need to know what their average velocities are right now, or not just stars, but gas and dust and things like that. And that we can get from the Doppler effect. This is what Vera Rubin and company did back in the 70s. They looked at the Doppler-shifted radiation from things at the outskirts of galaxies to measure their velocities. And then on average, those velocities are going to be the rotational velocity that you need to stay in orbit. There's some assumptions there, right? That it's more or less equilibrated and so forth. But nowadays, we have better evidence for dark matter than that. And we find out that those assumptions were more or less on the right track. Daniel Donaldson says, with all the discussion around marvels of ChatGPT and other AI, do you think that if they decide to answer all questions, quote, until you fix the climate issues, nothing else matters, climate change deniers will finally accept the truth? My guess is no. However, as a bonus, if you answer this question, your YouTube will go through the roof. So I think that both no, they will not do that, and climate change deniers will finally not accept the truth, and it will not cause my YouTube numbers to go through the roof. None of those things are true. But also, the reason why I'm answering this question is It's not true that until you fix the climate issues, nothing else matters. Even if you think, which is at least a respectable position to have, that fixing climate change is the single most important thing, we can multitask, we human beings. We have the ability to do more than one thing at a time. I'm not on the side of people who believe that you shouldn't do other good things just because this good thing still needs to be done. We should do all the good things. I think that we have the capacity to do at least many good things all at the same time. Dave Grundegeiger says, layman physics enthusiast here with a year of general physics in college and a lifetime of pop-sci reading. My question is, since gravity warps space-time, what does it mean when we talk about fractions of a second after the Big Bang? How can we talk meaningfully about a second in that extremely warped space-time? How does it relate to us here and now? How should we think about it? Well, there's different ways to answer this question, the most basic one of which is to say that there are different ways in which space-time can be warped. In particular, if you look at the space-time of an expanding universe in general relativity, the kind of space-time, the so-called Robertson-Walker metric that we use to describe the universe to a good approximation in general relativity, space can be warped, but time is not. Time is just time. One way of thinking about how this could be true, if there's so much matter and energy near the Big Bang, is if you say that time is warped, you have to say compared to what, right? When you're talking about time as a dimension and measuring distances in that dimension, you're talking about what clocks read. And so what do clocks read compared to what? There is something called a second. And if you have a clock, whether it's from some atomic clock, from some atomic transitions, or a mechanical clock, and it ticks off a second, even if that clock is near the Big Bang and therefore surrounded by other matter and energy, all the other matter and energy is also surrounded by matter and energy, and it's all in the same situation. So everything that feels the passage of 1 second is going to feel the passage of 1 second and measure it to be 1 second. So there's no difference between clocks doing one thing and clocks doing another thing. That's in contrast to a black hole or even the gravitational field of the Earth, where you do have a difference. If there's a clock that is hanging out near the event horizon of a black hole, that's different than a clock that is over here. So you can have different amounts of time elapsing on those two clocks if you were to compare them nearby. This is just another way of saying that even though the universe is rapidly expanding near the Big Bang, it's homogeneous and isotropic. So it's the same throughout space. So there's no difference in how time is passing from place to place. Qubit says, why is it that even though we have understood the process of decoherence, in particular within the framework of quantum Darwinism, scientists still talk about the measurement problem as completely unsolved? Why isn't that explanation sufficient? And what is still missing in order to settle the debate? So what's missing in order to settle the debate about the measurement problem is you still need to talk about the foundations of quantum mechanics. You need to have an ontology. And people don't agree on what the ontology is. So to go back a little bit, for those who are not experts, by decoherence, what we mean is that if you try, like Schrödinger tried with the Schrödinger cat experiment, to set up a situation where you put not just a microscopic thing, like an electron or an atom, into a quantum superposition, but to try to put a macroscopic thing into a quantum superposition, like an awake cat or an asleep cat. Decoherence is the fact that macroscopic things, or even sometimes microscopic things, but certainly macroscopic things, are constantly interacting with their environment, with the air in the room, the photons in the room, and so forth, the infrared light given off by warm objects all around you. This is all stuff that is interacting with you, and if you're a macroscopic object, that stuff interacts with you differently depending on which part of the superposition that you're in. If you're an awake cat or an asleep cat, different photons will hit you and be absorbed. So you become entangled with the environment very, very quickly, and that's decoherence. It's a well-known fact that if you let decoherence happen, and then you look just at the quantum state of the system, so you forget the environment, okay? You ignore it, that's constructing the density matrix that we talked about earlier. Construct the density matrix for the system, tracing out, as we say, the environment, ignoring the environment. Then, because of decoherence, it's well known that the elements of the density matrix take the form of a probability distribution. They are numbers between 0 and 1, and they add up to 1. and they act for all the world like a probability. And in fact, in the case where you were just going to be a Copenhagen person and say the probability is the wave function squared, the probability of collapse onto something, that is the number that you get in the density matrix, that wave function squared. So what you have after decoherence, described by the density matrix of the object, is an ensemble of different states weighted by their Born rule probabilities, okay? So therefore, it is, for all intents and purposes, as if there's a probability distribution over these measurement outcomes. But that doesn't mean that it is a probability distribution over these measurement outcomes. You need an extra sentence or two or three. So one extra sentence might be that that whole quantum state, whether it's the pure state before or the density matrix after, represents real parts of reality, okay? That the different parts of the density matrix are all simultaneously real. That's what you would say if you believed in many worlds, if you thought many worlds was the best theory. They're all different branches of the wave function weighted differently in the density matrix. But you could also say that some magical thing happens and there is only one element of the density matrix that truly represents reality. And what those elements of the density matrix are telling you is just the probability of being in one or the other. That would be a different physics. That would be different laws of nature, okay? To erase the other terms in the density matrix and to point your finger at one of them and say, this one is the real world in which we live, fine. You have done something. You've made a new theory of physics. But tell me exactly when that erasure happened. That erasure is just the collapse of the wave function. So everyone agrees that decoherence gives you a probability distribution, but what they don't agree on is the physics underlying what is going on, and the physics still matters. Okay, I'm going to group together two questions. One is from Emmett Francis, who says, do you have a typical response to the claim often made by Christian apologists that materialism/physicalism is self-defeating? For context, the basic idea is summarized in a C.S. Lewis quote as, if naturalism were true, then all thoughts whatever would be wholly the result of irrational causes. It cuts its own throat. And Brendan says, how do you respond to people who say that the laws of nature, the forces of gravity, electromagnetism, etc., are so persistent and consistent that it must have had a creator? To me, this sounds like a similar argument of why there's something rather than nothing. Curious to hear your thoughts on it. So both of these, I don't know why, this happens sometimes in the AMAs where we get similar questions just out of the blue from different people, even though I didn't talk about these things recently, but that's fine. They both are different aspects of what I think is a pretty common impulse or intuition, I'm not quite sure what to call it, feeling among people who are not physicalists, materialists, whether they're religious or something else. They want there to be a certain kind of explanation, or even, I would go so far as to say, a certain kind of governance in how nature works. They don't want to think that it is possible for nature to just be. And they get this impression by dealing with little subsets of nature that we deal with in our everyday lives, right? You know that if you have some machine like your car or whatever, and you don't constantly maintain it, it's going to break down. And you also know that that car didn't just pop out of existence randomly. So in the real world, in our everyday lives, when we see structures that are organized and working towards some purpose and so forth, they're always maintained for some reason by some intelligent agent and so forth. So the mistake that these people are making is saying, therefore, I expect the universe and all of reality to follow that same paradigm. So in the C.S. Lewis quote, he says, if naturalism were true, then all thoughts whatever would be wholly the result of irrational causes. So how do we interpret what he's saying there? It's not the clearest statement ever made, but the thoughts are going on in your brain, and he's saying, look, if you're just natural, if you're just physical, like the physicalists would have you believe, then that's just, things bumping into each other. There's no guidance there. There's no reason why the particular things should be bumping around in your brain in the particular way that they are. And the reason why I say that the sentence is not clear is because it's not quite clear what the objection is. Maybe he said it elsewhere. It's a tiny quote. I'm trying to be fair to Lewis, but I can imagine two different true objections to this. One is the sort of initial conditions question that the particular neurons firing and so forth that are going on in your brain don't have any reason to represent or reflect reality, right? I mean, they're just bumping around in your brain. But I think we know the answer to that. I mean, through various things with evolutionary biology and the laws of physics and so forth, there are perfectly good reasons why the actual thoughts we have in our brains as coming out of the physical processes in our brains should correctly reflect the outside world. We talked a little bit with Andy Clark about this just last week. People try to make arguments. Well, if evolution were true, then our brains and our bodies would just be maximized for survival, not maximized for truth. Well, yeah, but truth is really helpful to survival. Correctly understanding how the world works and what's going to happen is actually really helpful if you want to make it from day to day. So in that sense, I don't think there's any argument as to why the things that are going on in your brains should reflect correctly the outside world. The other possible construal of this sentence that I could imagine is the very action of the neurons in your brain or the atoms in your brain that allows them to reflect the outside world relies on the laws of physics being obeyed, right? In other words, the things that happen in your brain aren't truly random from moment to moment. They follow the patterns that we call the laws of physics. Why do they do that? Why is there any regularity to the world at all? And it's a reasonable question to ask, but the unreasonable thing would be to have a presumption that you need something to hold it together, need something to enforce the laws of nature, right? The word law makes you think of the analogy with actual laws passed by governments and so forth, and laws need an enforcer, right? They need a legislature and they need enforcement mechanisms. But that's just a bad analogy. I mean, that's not a really rigorous argument. It is a true fact about nature that it has patterns in it, that it obeys laws. I have no way of judging whether that should be surprising or whether that should be the most natural thing in the world. But it is what it is in the world. And to say, and it's because God did it, in my mind, adds nothing to our understanding of it. So same thing is true for, that's basically exactly what Brendan was getting at, the idea that the fact that the laws are so consistent and persistent, there must be a creator. Why? Why did you ever get that idea? I can imagine that you're just incorrectly porting over intuition you get from dealing with cars and so forth in your everyday life. But the universe isn't like that. I have no reason to think that it being law-like is any weirder or more surprising than it would be if it were not law-like. Maybe someday we will know, but now we certainly don't. Paul Hess says, in the April AMA, you talked about whether the concept of emergence can be used with respect to human societies. This made me curious to hear your thoughts about an adjacent topic. Do you subscribe to the great man or great person theory of history, where individual leaders drive the course of human history, or do you subscribe to something more like historical materialism, where the bulk forces like economics, technology, and culture drive the evolution of human history? Well, I think if you go way back into the archives of the podcast, you'll find a conversation with Ed Watts, who is a historian of the Roman Empire. And that conversation was, I guess I should include that more. Sometimes people ask, like, what was the podcast episode that changed your mind the most or gave you the most ideas? That should absolutely be one of them. Because if you go back to the decline of the Roman, I might have said empire, what I meant was the decline of the Roman Republic, the turning of the Roman Republic into the Roman Empire. Why did that happen? And Ed Watts tells a story. It's a version of a story that plenty of other people have told about the Gracchi brothers and them assembling mobs to intimidate the Senate and things like that. And I asked, isn't that too much credit or blame, whichever you want, being given to just a small number of people? And isn't that too much like the individual great person theory of history? And I thought we moved past that. And his answer was, well, most of the time, you can imagine that any one person is not going to be able to affect the large-scale sweep of history that much. But there are crucial moments when things could go one way or the other, and the traditional deterministic historical materialism kind of considerations are not going to tell you what happens, and an individual can have a huge impact. And as a physicist, someone who knows about phase transitions and chaos theory and things like that, this makes 100% perfect sense. The thing about history, the thing about human beings, and this is relevant to the physics of democracy also, is that on the one hand, there are a lot of people. So there's some collective behavior when we think about history or society or democracy. But on the other hand, people are individually complex and hard to predict, and they interact with each other in very strong and unpredictable ways. So even though there are a lot of people, it's not like a box of gas where the individual particles in the gas are very simple-minded and linear in their responses. So I think that it depends is the answer. There absolutely are bulk forces like economics, technology, and culture that drive the evolution of human history to a large extent. But I think that if you sat down, we're nowhere near being able to do this, but if you sat down with those forces and tried to make predictions, you wouldn't end up predicting specific detailed historical events. You would predict trends and probabilities. And the different probabilities might describe very different trajectories. A tiny push right at the right moment can put society on a very different path. So I think it's both. I think there's a lot of deterministic historical materialism, and there's a place for individuals to have outsized influences at particular moments. Brad Malt says, do you think we'll ever be able to detect the cosmic neutrino background, and what might we learn if we could? So the short answer is I'm not the person to ask about whether we should do this or not. I'm not a neutrino experimentalist. I don't even know. I've heard people talk about detecting the neutrino background. For those of you who are not up on it, just like the Big Bang created a whole bunch of photons that we can now observe as the cosmic microwave background, it also created a whole bunch of neutrinos. If you might want to know why those two, why photons and neutrinos, they are the massless or nearly massless, very low mass particles that were in thermal equilibrium at early times and just stuck around as the universe expanded and cooled. There could be other low mass particles like axions, but they were never in thermal equilibrium. There are other particles like electrons that were in thermal equilibrium, but they mostly just annihilate away. So neutrinos and photons are most of the relic particles. So there is a neutrino background as well as a photon background. I hope we can detect it, but there's a technology question there, right? I don't know what the sensitivity of the detectors is. I will say we have very, very strong evidence for the existence of the neutrino background indirectly through cosmology, through observations of the cosmic microwave background and large-scale structure. In the early universe, when it was radiation dominated, there's a certain period where the photons and the neutrinos were most of the energy in the universe. And there's a certain period later where it's matter dominated, and dark matter and ordinary matter are dominating. But at that moment, when it was radiation dominated, and that includes the neutrinos as well as honest-to-goodness photons, the number of photons, the density of the cosmic neutrino background affected the evolution of large-scale structure. So not only can you absolutely see that there had to be neutrinos, you can put limits on their masses. If they were too heavy, then there wouldn't be enough of them to have the effects that they actually have. So you can put an upper limit on the mass of neutrinos that way. If you could detect it, it depends on the details of how you detect it, what we would learn. Otherwise, I don't have any great predictions about that. Vicky Ramsey says, I've heard you speak and write upon the subject of time dilation with regards to general and special relativity. As in, what is the correct way to think about the predictions of time dilation from a theoretical point of view? But I would love to hear your thoughts on actual time dilation experiments, such as the NIST 2010 and the more recent 2022 JILA experiments. My question is there anything about these experiments that causes you to update your priors? Short answer, no. I didn't expect that there would be, because these experiments are exactly what you would predict. The experimental results that we actually obtained are exactly what you would predict from general relativity and special relativity, and those are already very much baked in to what my priors are. The experiments are still worth doing, though, for two reasons. One is they can lead to technological advances that could be very important for various things, and even better for someone like me, maybe they wouldn't have agreed with the predictions. And if that had happened, that would very much cause me to update my priors, but it didn't. So far, all the experiments that have been done on time dilation, etc., have been very compatible with the predictions of general relativity. Sean Virtue says, am I correct in thinking that the number of dimensions in Hilbert space, the number of degrees of freedom in the universe, the number of possible variations of the wave function of the universe, and the number of possible arrangements of all particles in the universe are all the same number? You are on the right track, but not exactly correct. For one thing, let's just eliminate that last bit, the number of possible arrangements of all particles in the universe. The universe is not made of particles. If you want to ask questions about the fundamental nature of the universe at this level of specificity, you have to take into account that it's a quantum field theory universe we're talking about, not a particle universe. So in some sense, there's something like this, but you have to talk about the number of possible arrangements of all the quantum fields. And even there, it's not very accurate because probably field theory doesn't work all the way down to situations where quantum gravity and the Planck scale is important, things like that. So let's eliminate that clause from the statement. What you're basically getting at is there a relationship between the dimensionality of Hilbert space and the number of degrees of freedom or variations of stuff in the universe? And the answer there is basically yes. There's one very, very tiny footnote I will put there. If you have, let's say, a two-dimensional Hilbert space, okay, so a single qubit, how many degrees of freedom do you have? So you have a single qubit that can either be spin up or spin down. So it's a little vector that's pointing toward the spin up part of direction in Hilbert space or the spin down direction in Hilbert space. So you might say, well, I have 2 degrees of freedom. But of course you don't. You have a single qubit, right? If I tell you the amplitude, the size of the amplitude, the modulus, that is to say, of the amplitude of the spin up part, then I know instantly the size of the amplitude for the spin down part. So there's only 1 degree of freedom there, even though it's 2-dimensional Hilbert space. That's nitpicking. I'm not going to make a big deal out of it, but I take it from this question that nitpicking is encouraged, so that's what I'm giving you. Antoine Chopin says, you said you were busy book writing. Could you share with us what this process looks like for you since idea inception, I guess, since in the sense of ever since, idea inception to publishing? What are the main steps to write a book, and which ones do you find most least enjoying along the way? Well, you're in luck. A couple of years ago, I did a holiday message on exactly this. So you'd have to look it up, but at the end of 2021, maybe 2020, I forget. But I did a little solo podcast episode talking about exactly this. So you can get much more details there. The whole process it takes a very long time. You have to invent the idea of the book. You have to do a little research. You have to think about whether or not it's a good idea. I mean, the number of ideas I have for books is way larger than the number of books I will ever write. You have to get a contract with a publisher, the whole bit, get an outline, do research, write the book. And then you give the book to both your editor at the publishing house and your friends to read, and then you get comments and you revise. You get figures made. That might be the least enjoyable part, getting the figures made. Jason Torchinsky, who is a former Mindscape guest, is my favorite illustrator, and he is great. If you ever see any non-stick figure illustrations in my books, they've been done by Jason. You know, the picture of Maxwell's demon and so forth from Eternity to Here, one of my favorite images that he ever made, but there's many in the different books. But you have to get them done, and who has time for that? I'll tell you that the biggest ideas in the universe is a special challenge, because I know some of you can be groaning and some of you will think this is perfectly obvious, but publishing houses, trade publishing houses like my publisher Dutton, that is part of Penguin, will only take manuscript submissions in Microsoft Word. That's it. So if you're used to being a scientist and typing text with lots of equations, of course you're going to use LaTeX or some flavor thereof. And you're used to doing that, and it makes perfect sense, and it's meant for that, and it's easy, and it's almost as easy as just writing text. Putting equation into Microsoft Words is terrible. It's just, it doesn't work all the time, and it's futzy and whatever, and it greatly slows me down and causes angst when I'm trying to be on a roll and get text written, right? So that's annoying, but I get it. Usually, I won't even use Microsoft Word to write a book. I'll use Scrivener. Scrivener is a wonderful program that lets you keep the whole project in sort of separate subfiles. You have one big document that is your whole book, but you can have separate subfiles for different chapters and for PDF files and figures and resources. And Scrivener is very, very helpful for organizing that. And then you can output the parts of it that you want to output as a Microsoft Word document. But that only works if it's all text. Once you get to equations, Scrivener is not up to the task. So yeah, this one is more painful than the average. And then of course there's copy editing, and you have to record the audiobook, and then you have to give some talks when it comes out. Look, I like the whole thing. I love writing books. I mean, the thing that I'm really feeling right now, when I'm in the finishing stages of writing book 2 of The Biggest Ideas, which is Quanta and Fields, where I actually do not that much quantum mechanics. Well, it's all quantum mechanics, but quantum mechanics as quantum mechanics is just going to be a quick 3 chapters at the beginning. And then quantum field theory and particle physics and Feynman diagrams are most of the book, as they were for the videos. And I really love explaining it, getting it right, thinking about it. It's work because, you want to say this. Is that the best way of doing it? That's the way that all the physicists do it, but is it the best way to be understandable to people who are not physicists? It's a fun kind of challenge and puzzle. And, I succeed halfway, maybe. I don't succeed all the way, but I'm trying and I'm learning things myself along the way. Andrew Goldstein, David Wolpert recently wrote an essay on how to study concepts beyond imagination, a plane of knowledge beyond the grasp of human minds. I was intrigued by the notion that advances in artificial intelligence might reveal fewer cognitive limits than human thoughts and perceptions. Do you have any thoughts on Wolpert's suggestion? Well, I know David very well. I think he's a brilliant guy, but I haven't read that essay that you're pointing to. I will say 2 things. I think there's not having read the essay, so not knowing what David is talking about, there's 2 different questions. One is, are there statements that would qualify as knowledge, right? True statements about math or physics or whatever that could be generated artificially that a human mind couldn't grasp even after they had been generated. I don't think that's going to be true. Maybe this is a lack of imagination on my part. Very, very possible. I could have my priors, my credences dramatically changed. But I think that anything out there that is understandable by human beings. I think there's a sort of threshold of cognitive ability that you can understand statements within the worlds of logic and math and physics and science and so forth. And we human beings can do it. It might be hard. Some statements in physics as we understand it now are harder to understand than others. But I don't think that there's any true limitation to human beings' ability in that direction. The other question, though, is the ability to come up with such statements. I'm 100% of the belief that artificial thinking machines might be able to come up with statements which we human beings didn't. I don't think that the current generation of very impressive large language models are going to do that. In fact, I played with them quite a bit, precisely wondering about this question. Can you use large language models, GPT-4 or whatever, to answer difficult questions? No, you can't. Difficult questions that have not yet been answered by human beings. Because all they do is take what human beings have done and use that to make a predictive language model, right? So if you try to trick it by giving it the Sleeping Beauty problem or something, it knows the Sleeping Beauty problem. It's read about it on the internet. So it just gives you the answers and it'll say, well, we're not sure about what the answer is, okay? It's very hard to get truly new insight from a large language model. But that's not to say that different kinds of computer intelligence couldn't do it. So yeah, that I'm very excited about, the possibility that there are kinds of thinking and kinds of conclusions that can be reached by AI in the years to come. Anthony Robo says, we are a mere 4 years away from the 100th anniversary of the 5th Solvay Conference. What do you feel would be a particularly special way in which the world's community of scientists and thinkers could commemorate such an amazing event? Well, that's a great question. I'll tell you why it's a great question. I mean, there's a sort of down-to-earth aspect of it, which is how do you commemorate a big event? Okay, and I'm not going to go into too much about that, but here's the thing. The reason why we cared so much about the 5th Solvay Conference is because we more or less cohered on an understanding of quantum mechanics, the understanding we currently call the Copenhagen interpretation, right? It was truly focused on what we would now call the foundations of quantum mechanics. That's what everyone cared about. Einstein and Bohr and Schrödinger and Heisenberg and Pauli and all those folks who were there. And that at the time, in 1927, that was the forefront of physics, the most exciting topic. Very few of the people who you would recognize today as the world's most famous leading physicists think that the foundations of quantum mechanics is a forefront topic that we should be spending a lot of time on. I think that, and a few of my friends think that, so if you're a common listener to Mindscape, you might get a distorted idea, but it's not a very high prestige subfield within physics as it is currently understood. So what I would guess / predict / worry about is that if you tried to do a century later Solvay conference where we got the brightest minds in physics to talk about the most interesting topics, they would talk about their current interests, whatever they were working on, right? Whether it was in string theory or whatever, they were working on, and they would get some good talks and they'd be, interesting things, but it wouldn't be anything like the Solvay conference. Number one, because it's not about the foundations of quantum mechanics, so it wouldn't really be in the spirit of that. But number two, we don't have that consensus on what the interesting questions are right now, right? The reason why Solvay was so interesting is because everyone was focused on the same issues. And a lot of the work, a lot of the progress was made not during the talks, but at breakfast and at drinks afterward. Beer, Belgian ale was consumed in great quantities. And you cared about the same issues, right? You had this common purpose. And so you could try to commemorate the Solvay conference by bringing together people who had some kind of common purpose about something. Maybe it is the foundations of quantum mechanics, but those people talk to each other a lot already. It's not a moment, even though I care about the foundations of quantum mechanics, I'm not going to pretend that we are on the cusp of a breakthrough or even the cusp of bringing together a lot of disparate ideas to form some consensus, right? So that's what you would want. That's the kind of science you would want to really do justice to the spirit of the fifth Solvay conference. I'm a little skeptical that's ever going to happen. Probably a bunch of old farts just patting each other on the back. That's what's probably going to happen. Nalita S. says, when observing the universe and its components, it seems that its interior goes through an inevitable increase in entropy over time. Second law of thermodynamics. And incorporating the mind-boggling cosmological multiverse idea into this leads one to wonder if our universe itself undergoes as a whole an increase in entropy over time, and how would the expansion of the universe affect this process? Well, you have to sort of divide this question into two different things. One is the multiverse aspect, and the other is the expansion of the universe aspect. These are two different aspects. So if you just think about our observable universe, so put aside the multiverse for a moment, think about the universe we live in and the universe we see. It is increasing in entropy as a whole, yes. And in fact, one of my favorite papers that I ever wrote that doesn't get nearly as much attention as I would like it to, because it gets a result that everyone expected was true already, was my paper with Aidan Chatwin-Davis when he was a grad student at Caltech. And we showed that you could think of the cosmic no-hair theorem as the second law of thermodynamics. So the cosmic no-hair theorem was first proven in some cases by Bob Wald back in the 1980s, and it says that, analogous to the black hole no-hair theorems, that say that if you make a black hole and it's all lumpy and things, those lumps kind of quickly shake away and you settle down to a black hole having no hair. In the presence of a cosmological constant, the universe does the same thing. This is Wald's point, that everything empties out, all the galaxies and so forth smooth out and it gets scattered to the four winds, and you're left with an empty universe with a cosmological constant, what we call de Sitter space, and a universe that has no hair. All such universes are going to look the same once you tell me the value of the cosmological constant. That always sounded to me like equilibration and thermalization, or whatever you want to call it. So Aidan and I proved a theorem that you could think about. I mean, it's a very, very minor theorem under very, very oversimplified assumptions, but you could do better, hopefully. If you don't say anything about Einstein's equation or general relativity, but instead you say the universe increases in entropy up to a maximum value and then stays constant. We borrowed a definition of entropy in an expanding universe from two former Mindscape guests, Netta Engelhardt and Raphael Busso, and we showed that simple conjecture that the universe expands in entropy, not in space-time, but expands in entropy, and then goes to a constant, that also implies that our future space-time metric is de Sitter space, just like general relativity says. So you can think of that approach to de Sitter space as equilibration and increase in entropy. It all makes sense. But that's only like one little part of the universe, right? Outside the universe we observe, lots of things could be happening. I am in favor, or I like the idea that I've published about, which says that there is a multiverse, and at any one moment in time, with very, very large probability, there is a direction in time in which the multiverse's entropy is increasing. Even if individual parts of the multiverse settle down to constant entropy de Sitter space, you make more and more universe, and therefore you make more and more entropy, maybe even making more and more universes by making baby universes. And if you trace backward far enough, the same thing is happening, but in the other direction of time. So there's some moment where entropy is its minimum value, but that value could be very, very large. And both before and after that moment, entropy increases as you go away from that moment. But we don't know. That's a conjecture. That's a scenario, a model, whatever you want to call it. We don't understand the very, very ultra-large scale structure of the universe to really say with any confidence. Tarun says, I'm currently reading your Biggest Ideas book and particularly enjoy the parts where you stop to consider the philosophical implications. At one point, you question whether Newton's formulation of classical mechanics or the principle of least action is correct in terms of telling us what nature is doing. You propose that neither is correct, as nature is just nature and does what it does. But unless I'm mistaken, you appear to be more in the camp that believes physics tells us something deep about reality, rather than it being purely about building models and should not be taken literally. Why do you view this local versus global aspect of physics differently to how you view quantum field theory, for example? Well, it's possible I wasn't clear in what I was trying to say in that section of the book. I do believe that physics tells us something deep about reality. The point I was trying to make there when we're discussing Newton's formulation of classical mechanics versus the principle of least action is that these are not two different versions of reality. It's the same reality that is being described either way. So there's no argument about which one is truly right or truly wrong. They're mathematically equivalent to each other. They're different languages or different vocabularies for talking about the same underlying thing. So to say, well, I think that someday we'll discover that the principle of least action is correct and Newton's formulation is incorrect, that can never happen because you can derive one from the other. Thinking about nature in different ways can be very helpful because we don't know the fundamental laws of physics, and thinking about them one way or the other might help us propose new ones, but we're not looking for just the right one once and for all, forever. Nick Gall says, in your paper, Why Boltzmann Brains Are Bad, you base your argument against Boltzmann brains on cognitive instability, and you cite David Albert's book Time and Chance in support. I couldn't find any direct mention of cognitive instability in Albert's book, but he gives another reason for embracing the past hypothesis, namely that such an axiom is immensely fruitful. Quote, our grounds have to do with the fact that the proposition that the universe came into being in an enormously low entropy macro condition turns out to be enormously helpful in making an enormous variety of particular empirical predictions. So my question is, instead of dismissing Boltzmann brains and other possibilities invoking random fluctuations based on cognitive instability, why not base it on the fruitfulness of the past axiom instead, since the concept of fruitfulness better matches the criteria of theory choice as discussed by Kuhn and others? So this is a good point, and it's a slightly subtle thing. Let me see if I can answer it accurately. It is true I've actually talked with David about this because I absolutely got the phrase cognitive instability from David Albert. And the book that he wrote about entropy in the arrow of time is Time and Chance. But as we realized in talking to each other, he never actually uses that exact phrase in the book. He uses equivalent phrases. He talks about skeptical scenarios and therefore self-undermining scenarios. So self-undermining is kind of the same thing, or there's different ways of characterizing the same idea. The point is you cannot consistently both hold a belief and have good reasons for holding the belief in these scenarios at the same time. So I misattributed the phrase, but it is his phrase, so I didn't do too badly. I didn't steal the phrase from someone else. The more important question here is it the right phrase, the right idea to be pointing at, or should we point to fruitfulness instead? And again, there's sort of two little things that are closely related but not exactly the same that are worth saying. One is that there are slightly different questions being asked here. When I'm talking about Boltzmann brains, I'm basically contrasting the idea that we are a random fluctuation with the idea that we are not a random fluctuation. So any other scenario other than us being Boltzmann brains is being contemplated here. And in the particular case of Boltzmann brains, it is cognitively unstable, but the large set of alternatives, it would be hard to characterize them as fruitful because there's a lot of different alternatives, right? When we're talking about the past hypothesis, and here this is the other point, that's a very specific alternative. And as David correctly says, it is immensely fruitful. But by itself, I don't think that gives us license to accept it if we were believing that if we had a high prior credence on randomly fluctuating universes. Precisely because if the universe were randomly fluctuating, there would be, and you conditionalized on finding observers who thought that there was a past hypothesis and thought that it was fruitful to think so. In a randomly fluctuating universe, the overwhelming majority of such observers are totally wrong. So it doesn't help you, right? It doesn't actually get you out of the dilemma you're trying to get in. You can't just say it's fruitful to imagine there's a past hypothesis. You have to give a positive reason for rejecting the random fluctuation scenario. And so I think that just the fact that if you believed that scenario had a possibility of being true, it would prevent you from doing anything else. You cannot possibly move forward using logic and reason and evidence if you think that scenario might be the universe in which you live. So I think we should reject it, whatever label you want to put on that rejection. Elijah Frisch asks another priority question. Hypothetically, if some future evidence or discovery help prove that Everettian interpretation is correct, what do you think that discovery could look like? Conversely, in theory, what type of discovery or evidence might persuade an Everettian toward a different interpretation of quantum mechanics? Well, there's sort of a fanciful answer to this and a more realistic answer. The fanciful answer is, if you could talk to other universes or if you could detect them in some way, that would be a discovery that helps you do it. Of course, by the actual mechanics of Everettian quantum mechanics, that is so incredibly unlikely to happen that even if it did, you would probably say it was probably something else, right? You probably wouldn't believe it even if you saw it. So I'm not waiting around for that to happen. But I've said this before, I'll just say it again. When you say the words Everettian quantum mechanics, what do you mean? You mean that you say that reality is modeled by a wave function or a quantum state or a state vector in Hilbert space, however you want to say it, and the only thing that wave function ever does is obey the Schrodinger equation, okay? That's the entirety of the Everett interpretation, its fundamental formulation. So there's a lot of evidence that it's correct. All the evidence we have that there are wave functions that they obey the Schrodinger equation, all that evidence counts as evidence for the Everett interpretation. What you want to do is compare it to alternatives, okay? And so if you have an alternative, you have to ask, how does that alternative differ from Everett? So back when we were talking about the density matrices and decoherence, if you literally have a physical mechanism that gets rid of other elements of the density matrix other than the ones you find yourself in, that's a difference than to Everettian quantum mechanics. And it's a difference with potentially observable consequences. And I'm sorry that, I don't mean to be grumpy toward you, Elijah, but I've made this point many, many, many times. There are theories where the wave function clearly does not always obey the Schrodinger equation, where it spontaneously collapses. Roger Penrose has such a theory, okay? We can look for that, and if we see it happening, Everett is wrong. He is falsified, and everyone would be very happy. Karl Popper himself got this. He never said that Everett was unfalsifiable. He didn't like it because he had his own favorite interpretation of quantum mechanics, but he liked Everett a lot more than he liked Copenhagen, which he thought was just philosophically nonsensical. Fabian Rosdalen says, from what I understand, you don't believe that P-zombies are possible. Is that correct? And in that case, what is your take on the question of moral consideration of AGI, artificial general intelligence? I can't think of any tests that would indicate whether or not AGI is really sentient or if it's just in a hypothetical case where the AGI is behaving as if it were sentient. Well, that's my point. My point in saying that P-zombies are not possible is that if you actually had a physical system that behaved in every way exactly identical to that as a conscious creature would behave, then it's conscious. The tricky thing there is the every way thing, right? Now, how do you know that your physical system behaves in every way like a conscious creature does rather than just in some ways? That's why we worry about the Turing test or whatever. But my point about P-zombies, philosophical zombies, is the thing that is trying to be conceived is a being that thinks it's conscious. If you talk to it and say, are you conscious? It says yes. If you say, like, are you experiencing the redness of red? It says yes. It will describe to you what that is like. We know that because it acts exactly like a conscious creature does. But then you somehow imagine that it's wrong, that it's not lying to you, but it's sincerely misinformed about its own inner mental states. And I don't think that that is a plausible conception. If it were, this is another self-undermining argument going on here. If it were, then you would have to admit that our introspection about our experiences is utterly unreliable. Because a zombie thinks it's introspecting about its inner experiences, and apparently you're saying it's not getting the right answer. So that's not good evidence of anything. So I say the same thing about artificial general intelligence, that if it's doing something, if it's behaving in the same way as a conscious creature, then it's conscious. But the behavior is really not just like getting up and walking. It's all of the things going on in its brain, whatever that brain is. It's the believers in P-zombies who beg the question by presuming that it's possible to imagine something that has all the behaviors of a conscious creature yet doesn't have conscious experience, which is cheating. Simon Hayward says, radioactive decay occurs with a known half-life, so the number of events is easily predicted. However, from the perspective of a given atom, the received wisdom seems to be that this event is random. Is this actually true, or does the apparent random nature reflect some missing knowledge of the state of the individual atoms? Well, I think it's really true. The statement in conventional quantum mechanics is it's really true. Of course, there are some people who believe in hidden variable theories of quantum mechanics, and so they say there is some missing knowledge there. But they will also say it's not only missing knowledge, it is inaccessible knowledge. Until you see the atom decay or not decay, you can't say whether it's going to. That knowledge is inaccessible to you. That's a part of hidden variable theories. Nikola Ivanov says, is the mechanism behind the Unruh effect similar to Hawking radiation? Both create blackbody radiation, a thermal bath, the first due to an observer's accelerating reference frame in a vacuum, and the second due to the strong gravity field of black holes. Yeah, exactly. That was Unruh's idea. So for those of you who don't know, we have Hawking radiation, discovered by Stephen Hawking, or at least theoretically predicted by Stephen Hawking in 1974, I think. Near a black hole, the quantum state settles into a configuration where it is giving off radiation. Okay, and a detector could detect it. Unruh, Bill Unruh, thought about the space-time around a black hole, and he realized that it was actually very similar to a subset of the space-time in flat space. So in good old ordinary Minkowski space with no black holes, no gravity at all, if you cut out a wedge and look at just that wedge, it has many of the properties that a black hole spacetime does. I'm realizing now this is not helpful to you because it's a space-time wedge and you're going to be thinking of a spatial wedge and you're going to get the wrong impression there. But if you have a space-time diagram with X going left-right, T going up-down, light cones going at the diagonal, okay? So take the wedge on the right side of that figure. So the positive x-axis and values of time in between plus and minus x. So that whole wedge to the right of the light cone in the future is kind of like a future event horizon. The light cone in the past is kind of like a past event horizon, and the whole thing is very much like the space-time outside a black hole. And then he realized that if you were an accelerating observer, an observer that accelerated at a constant acceleration forever, you could stay inside that wedge forever. And to you, it would be like that was the whole space-time in which you lived. And then maybe you could imagine hand-waving your way into that conclusion, but Bill did the calculation. And what he showed is that it's a feature of quantum field theory in flat space-time that an observer accelerating at a constant acceleration sees a thermal bath of particles, even if they are in the vacuum. This is just a sneaky feature of quantum field theory in Minkowski space. It has nothing to do with gravity, but it's very similar to what gives rise to black hole radiation. So to Nicola's question, is it similar? Yes, and that similarity is entirely intentional. Craig Vandervest says, in a previous AMA, you mentioned that Baltimore has good restaurants. What are a few of your favorites? I think my single favorite is Alma Cucina Latina near the train station is really good, very inventive cuisine. You know, they'll give you sort of South American dumplings, but they're dumplings that look like gyozas, but they're South American and they're very, very tasty, and a whole bunch of sort of fun fusion cuisine things. What Baltimore is especially good at is sort of upscale casual things, like not super duper fancy Michelin star restaurants, but there is a French bistro called Duck Duck Goose, which I like very much. The seafood restaurants are amazing. If you want just the whole fish recently caught from nearby, prepared, in a very non-intrusive way, so you can really love the fish. Baltimore is super good at that. The Black Olive or Ouzo are Mediterranean restaurants that kind of do that. And there's fancier restaurants also. There's the Charleston is a famous fancy restaurant nearby. There's sort of an American kind of modern restaurant called Gunter & Co., which I like a lot. But anyway, there's a lot of restaurants that are really, really good. I should give a shout out to Cipriana, which is very close to Hopkins, which is a kind of Greekish restaurant, but again, kind of casual pub feel, but a great place to just hang out, get some really good falafel or lamb or what have you. Josh Charles says, if gravity is the result of curved spacetime, why are gravitons a thing? Well, because gravity being the result of curved spacetime is an entirely classical statement. That's what general relativity tells you, and general relativity is a classical theory. Gravitons are what happen when you quantize gravity, and we don't have the once and for all full theory of quantum gravity, as I'm sure you've been told, but we have no problem looking at weak field, tiny variations in the curvature of spacetime and quantizing them. And what you get are gravitons. I mean, you could exactly as well say, if electromagnetism is the result of the electric field and the magnetic field, why are photons a thing? It's the classical theory versus the quantum theory. In the quantum theory, you quantize the field and you see particles. Paul Conti says, as a British/European follower of your podcast, books, etc., I find it very difficult to understand the American obsession with guns and firearms and the Second Amendment. While I appreciate the historical origin of the Second Amendment, like most Brits, I am utterly astounded at the huge number of U.S. gun deaths every year, whether deliberate by accident or in suicides. What is your opinion of gun control, and do you own any guns yourself? So, I'm sure it must look weird to the outside world. We've talked about guns a couple times on the podcast, Andrew Papachristos most obviously. But it is true that the United States is singular in its obsession with guns. And I think, like many of these things, there's kind of a perfect storm going on here. The Second Amendment was, like many things, well-intentioned. People were very worried at the time, the late 18th century, in the tyranny of the government and the government using its military might to step in and taking freedoms away from the populace. The idea of democracy and self-control and self-representation and self-determination were not taken for granted back then. So they wrote in and remember, if you're European or British, maybe you don't know, but we had, after the Revolutionary War, a government called the Articles of the Confederation, which tried to just be a very loosey-goosey arrangement where the individual states were the actual centers of control, and they got together to talk things over under the Confederation. It didn't work. States got together and they just argued with each other, and it didn't form a whole sensible country. So there was a campaign to get a constitution that would really give us a strong federal government that could organize the country. Not everyone was on board, right? I mean, that's one of the things that made Alexander Hamilton famous, was contributing to the Federalist Papers, which tried to convince people that this constitution, which would really make us a whole single country, was a good idea. And one of the things that many people, including Thomas Jefferson and others, argued is that the Constitution as written just said what the government can do and how the government works. It didn't say what the government can't do. It didn't have a Bill of Rights. So the Bill of Rights was put in later. I mean, not that much later. It was part of the original adoption, but it was written after the Constitution was drafted as an attempt to lay out some of the rights. And so in the Second Amendment, it says the idea of a well-ordered militia is very important because the people can get together and resist a tyrannical government. So therefore, the right to own arms, the right to bear arms, should not be infringed. It's right there in the amendment that the point of this is to have a well-ordered militia. But anyway, what it concludes is saying, therefore, the right to bear arms should not be infringed. So take that as maybe a slight accident of history in how the exact wording of this amendment was drafted. And now, there's political game theory that goes on. Sure, plenty of people in the United States go hunting or whatever, or have a gun in their house for personal protection. But you could imagine being allowed to do that without making a whole thing out of it. In the United States, we very much make it a thing. It's a part of your identity for some people. Politicians running for office show pictures of themselves at Christmas with their family where every member of the family is holding a gun. And that's just bizarre and a little weird, but it's part of signaling that you're a member of a certain tribe. And the liberals are never going to take away my guns. And there's a positive feedback loop that gets more and more guns out there. So I don't own any guns myself. I am not, afraid of guns or think that they could be a bad thing. I think that, or think that they necessarily are always bad and should be banned and eliminated. But certainly they should be controlled and regulated at least as much as a car should be. It's much easier to get a gun in the United States than it is a driver's license, and that's just wacky and weird. By the way, it's also much easier to become a police officer than it is to get many other jobs in the United States. The amount of training and prerequisites for being a police officer in the U.S. are very low. And we see the impacts of that, right? So I don't own any guns myself, but again, I could imagine owning a gun. I don't have any special desire to do so. I don't think it's evil, but certainly there should be not only background checks, but you should have to pass some kind of exam, just like you do for driving. And right now you don't. Right now it's not like that. And there are so many guns out there that it's going to be difficult to lower the amount of guns that we have in the United States and to bring them under some kind of control. Peter Blankenheim says, Yang-Mills theory is such an important cornerstone of all modern physics. For those of us who have a rough understanding of tensor algebra, could you briefly encapsulate what is conceptually at the core of this algebraic truth and why it is so important, specifically how it can unite the weak nuclear and the electric fields? Well, I won't go into great detail here because I'm writing a book on it. Yang-Mills theory is going to be it's going to be one of the chapters in Quanta and Fields, the second volume in The Biggest Ideas in the Universe. And of course, that means that you can find the video, right? I did a whole video on symmetry and gauge theory. In fact, maybe two different videos, one on symmetry, one on gauge theory, one on topology and geometry, which is also important. But if you go through these videos, you will be introduced to the basics of Yang-Mills theory. For those of you who don't know or don't want to watch the videos, Yang-Mills theory is a generalization of electromagnetism. So electromagnetism, E and M, is, as we discovered after the theory was invented, it can be thought of as arising from a certain symmetry. You can think of a charged particle like an electron. It has a wave function, right? And that wave function is a complex number. and it can be rotated. You can rotate a complex number. A complex number is a plus ib, where a and b are real numbers. I is the square root of -1. So you can rotate a little vector in the complex plane, and there's no physical effect of that happening. What happens in electromagnetism is you can do that rotation separately at every point in space-time. So basically, there's an arbitrary choice at every point in space-time as to what you call the real part of the electron and what you call the imaginary part of the electron. You need both, but which is which doesn't matter. In fact, you can make it 2/3 this and 1/3 that, etc. Okay? And you can do that separately at every point in space-time. How do you know how to compare an electron at one point in space-time and another point in space-time? You need what is called a connection. You need one way to transport the value of the electron field at one point over to the other points. You can compare them. So you can say, are they the same charge or opposite charge or whatever? That connection, that information in between the 2 points in space-time is a field, and that field gives rise to the electric and magnetic field. It's called the gauge field, and it gives rise to both the electric and magnetic fields by just taking derivatives of them. Anyway, this might be over the heads of some of the listeners, but we're getting near the end of this long podcast, so that's okay. What Yang-Mills theory does is it just generalizes that. So instead of saying there's an electron and it has a wave function or a field that has a real part and an imaginary part, you say there are quarks. And quarks can be red, green, or blue, right? 3 different colors. So really, by the way, they don't tell you this, but it's not true that quarks can be red, green, or blue. What the truth is that quarks are a vector in a 3-dimensional color space. Red, green, and blue are fanciful names for the axes of 3-dimensional color space. There's the red axis, the green axis, the blue axis, and a quark is just a vector pointing in any direction in that 3-dimensional space. But what you call red, what you call the red direction, what you call the green direction, what you call the blue direction is completely arbitrary. You can rotate your basis vectors. And that's exactly, and now you're just going down the same story. If you have 2 quarks at 2 different positions, how do you compare them? Well, you need a connection field in between that tells you how to compare them. That connection gives rise to a force field, which in the case of quantum chromodynamics is the gluon. In the case of the weak nuclear force, it's the W and Z bosons, etc. So basically, Yang-Mills theory, I know this is probably incomprehensible to anyone because it's too short, but I encourage you to watch the longer video if it's not, or buy the book when it comes out next year. The short version is there is a symmetry because nobody cares what you call red, what you call green, what you call blue. But the way to both have that symmetry and nevertheless let yourself compare what's going on at different points in space-time requires the existence of a new field, which acts like a force field that we call a gauge field that gives an interaction between the different particles in the standard model. Okay, I think I'm becoming less coherent at the end of this long day, but that's okay. We're near the end. 2 more questions left. One is from Ash Wright. Are there any subjects for which your thinking has evolved enough in the past few years that readers of your books or listeners to early podcasts might want to take in with an extra grain of salt? You know, my opinions change over time. I just mentioned the insight I got from Ed Watts's podcast on the fall of the Roman Republic, but I don't think that you should be taking any prior podcasts with grains of salt. Because it's the process. It's the journey, not the destination. Trust the process, as I will say again in a few seconds. You know, I think you can learn things from any of the previous episodes. Very often in previous episodes, I have people on who I don't agree with about things, but I will always try to have people on who I think it is useful and productive to talk to, whether I agree with them or not. And almost always, I think I succeed in doing that. So I don't think it's about grains of salt. I think it's about you should always have a grain of salt when you're listening to anyone, podcasting about anything. Listen to what they say and ask how well it fits with other things you know, what questions you have about it, how much of it sounds trustworthy, etc. And finally, Attila Bartha asks, do you think the 76ers have a chance to beat the Boston Celtics without Joel Embiid? So background, for those of you who are not NBA basketball fans, it's the last question of the podcast of the AMA. I can talk about whatever I want. So I'm a huge basketball fan, NBA fan, and my team ever since I was a youngster is the Philadelphia 76ers. And this year, the 76ers are very good. Another team that is very good is the Boston Celtics. And these two teams have been historic rivals. I just saw the statistic recently that the Sixers and Celtics have played each other 22 times in the NBA playoffs, which is the most of any two teams in the NBA. In fact, the next most is only 14 times for the next most frequent pairing in the NBA playoffs. Going back to Wilt Chamberlain versus Bill Russell, Julius Erving versus Larry Bird, Allen Iverson versus Paul Pierce, and now we have Joel Embiid versus Jason Tatum, and there's other very good basketball players on both teams. In fact, I'm recording this on Wednesday, May 3rd. Just last night, we learned that Joel Embiid was awarded the Most Valuable Player Award, the MVP award for the NBA, which I think is well-deserved. And it's very cute. You can see videos online, and Embiid was literally in second place for the MVP award 2 years prior to this. So he's been so close without getting it. And he knew it was coming. Everyone who votes for the MVP tends to spill the beans ahead of time what their vote is, and many of them had said they were voting for Embiid, so we kind of knew it was happening. And he still broke down and cried when the news came out. Embiid has been through a lot. He discovered basketball late. He was born and raised and grew up in Cameroon. He didn't pick up a basketball or hear about it until he's 15 years old. A lot of the kids in the United States start playing basketball when they're 5 years old and are trained ever since. So he was very bad, but he was very tall and very athletic. He was a volleyball player and a soccer player, so he got recruited. And then he got injured. He missed not just the first year, but the first 2 years of his NBA career. And while he was sitting on the sidelines not playing because of injury, his younger brother, Arthur, back in Cameroon, was killed in a car crash. And Embiid came very close to just quitting basketball and never playing. And he did start playing and is very, very good, one of the best players in the NBA. And yet he has been subject to bizarrely unpredictable injury luck. His own teammate hit his face with his teammate's shoulder, and he cracked his face and had to wear a mask 1 year in the playoffs. Just last year, some player on the other team hit him in the face again and gave him a concussion and again hurt his skull, and he came back but didn't play very well. This year, he sprained his knee in the first round of the playoffs. And so my update here Wednesday, May 3rd is the 76ers played the Celtics in their playoff game on Monday, and they won. They won in Boston without Embiid in just one of the most entertaining basketball games I've ever watched. Tonight is game 2, and Embiid just proclaimed that he's going to play. He's well enough again to play. I sincerely hope that he is well enough to play. I don't want him to hurt himself again. I would rather not win any more games than have him hurt himself again. I'd rather keep him healthy for the future and for his own future, but we'll see. I mean, the medical staff and the coaching staff wouldn't let him play if they didn't think that he could run and jump and generally be healthy, so fingers crossed on that. But by the time you hear this, in between when I record it and when you hear it, there will be at least 2 more basketball games played between the Sixers and the Celtics. 3 more. It's Wednesday, so there's Wednesday, Friday, and Sunday. So there's 3 more. So the series might be over if the Sixers win all their games. That's unlikely. I pretend that it's likely because I'm a fan more than I am an analyst of basketball games. But or we could be down 3-1. We could be on the brink of elimination. You never know. That's why one of the reasons why sports are so much fun, because it is literally not predictable ahead of time. So to the actual question, Attila, do the Sixers have a chance to beat the Celtics without Embiid? The answer is always yes. Just like when people ask physics questions, is it possible that? The answer is always yes, it is possible. The answer is always yes, a good NBA team has a chance to beat another good NBA team. They just did it on Monday. With Embiid, they'll play much better defense and they have an even better chance of winning. It's still possible the Celtics have a chance to win all the rest of the games. There's always a chance. I just want to enjoy it. I want to have fun. The Sixers have a great chance this year to win. If you literally, as of this moment when I am talking, if you go to 538.com and look at their Odds for winning the NBA title, the Sixers have the largest odds of any team right now. Still not greater than 50%, though. And, things can happen. Freak injuries could still happen. It's unpredictable. Let's enjoy the journey. Let's enjoy the ride. Let's trust the process. Go Sixers. I'll be back a month from now. And if the Sixers are in the finals a month from now, I might just do a much shorter AMA, or I might just do a wholly basketball-focused AMA. Who knows? We'll find out then. Thanks for listening. Bye-bye.